Hi there. Let's begin the podcast with a gentle journey into one of nature's most remarkable phenomena. For over 4 billion years, our planet has maintained temperatures within a narrow range that allows liquid water to exist, life to flourish, and complex ecosystems to develop. This isn't luck or chance. It's the result of an intricate network of physical and chemical processes that work together, creating what scientists call Earth's climate regulation system. As you settle in and let your mind wander through these natural rhythms, imagine our planet as a delicate instrument, constantly tuning itself through forces that operate on scales both vast and intimate. From the microscopic interactions of gas molecules in our atmosphere to the slow dance of continents across geological time, everything contributes to maintaining the conditions we call home. The story begins, as all Earth stories do, with our sun. Every second, our nearest star releases an enormous amount of energy, sending light and heat racing across the 93 million miles of space that separate us. This energy arrives at Earth's atmosphere at a rate of about 1,361 watts per square metre, a measurement scientists call the solar constant. But this constant isn't quite constant. It varies slightly with solar cycles, and more dramatically over the long arc of Earth's orbital dance around the Sun. When this solar radiation reaches our planet, it encounters the first of many regulatory mechanisms. About 30% of the incoming energy is immediately reflected back into space by clouds, ice, snow, and other bright surfaces. This reflection, called albedo, acts like a planetary mirror, determining how much energy Earth actually absorbs. The remaining 70% penetrates our atmosphere and warms the land, oceans, and air. But Earth doesn't simply absorb this energy and grow ever hotter. Instead, it radiates energy back into space in the form of infrared heat. The balance between incoming solar energy and outgoing infrared radiation determines our planet's overall temperature. When these two forces are in equilibrium, Earth's temperature remains stable. When they're out of balance, our climate shifts. This energy balance might seem simple, but it's modulated by one of the most important temperature regulation mechanisms on our planet: our atmosphere. Without this thin layer of gases surrounding us, Earth would be a frozen world with an average temperature of negative 18 degrees Celsius. Instead, our atmosphere acts as a selective blanket, allowing most solar radiation to pass through while trapping much of the infrared heat that Earth tries to radiate back to space. This process, known as the greenhouse effect, occurs because different gases interact differently with different types of radiation. Solar energy arrives primarily as visible light and ultraviolet radiation, which pass easily through most atmospheric gases. But when Earth's surface absorbs this energy and re-radiates it as infrared heat, certain gases in our atmosphere absorb this outgoing radiation and send much of it back toward the surface. Water vapor is the most abundant of these greenhouse gases, and it plays a unique role in Earth's temperature regulation. Unlike other greenhouse gases, the amount of water vapor in our atmosphere is directly controlled by temperature itself. When the air warms, it can hold more water vapor, which increases the greenhouse effect and causes more warming. When the air cools, water vapor condenses out, reducing the greenhouse effect and allowing more cooling. This creates what scientists call a positive feedback loop, where changes in temperature lead to changes that amplify the original temperature change. Carbon dioxide, while less abundant than water vapor, provides a more stable foundation for the greenhouse effect. Its concentration in the atmosphere changes much more slowly than water vapor, making it a key player in long-term climate regulation. The amount of carbon dioxide in our atmosphere is controlled by a vast network of processes that operate on timescales ranging from years to millions of years. Plants and marine organisms constantly remove carbon dioxide from the atmosphere through photosynthesis, converting it into organic compounds and releasing oxygen as a byproduct. When these organisms die and decompose, much of this carbon returns to the atmosphere. But some of it becomes buried in soils or ocean sediments, creating a long-term carbon storage system that helps regulate atmospheric composition over geological time. The oceans play a particularly important role in this carbon regulation system. Seawater can dissolve enormous amounts of carbon dioxide, and the oceans currently hold about 50 times more carbon than the atmosphere. Cold water can hold more dissolved carbon dioxide than warm water, so changes in ocean temperature affect how much carbon dioxide the oceans can absorb from the atmosphere. This ocean-atmosphere carbon exchange creates another temperature regulation mechanism. When the climate warms, the oceans warm too, reducing their ability to absorb carbon dioxide. This leaves more carbon dioxide in the atmosphere, enhancing the greenhouse effect and causing more warming. When the climate cools, the oceans cool as well, allowing them to absorb more carbon dioxide from the atmosphere, reducing the greenhouse effect and promoting further cooling. But the oceans regulate Earth's temperature through more than just carbon storage. They also serve as the planet's primary heat distribution system. Water has an enormous capacity to absorb and store heat without large temperature changes, and the oceans contain about 1,000 times more heat than the atmosphere. This thermal mass acts as a buffer against rapid temperature changes, absorbing excess heat during warm periods and releasing stored heat during cool periods. Ocean currents carry this heat around the planet through a global circulation system that scientists call the Great Ocean Conveyor Belt. Warm surface water flows from the tropics toward the poles, carrying heat to higher latitudes. As this water cools in polar regions, it becomes denser and sinks to great depths, then flows back toward the equator along the ocean floor. This deep water eventually rises to the surface and warms, completing a cycle that takes about 1,600 years. This thermohaline circulation, driven by differences in water temperature and salinity, transports about 15 million cubic meters of water per second in the Atlantic Ocean alone. That's 15 times more water than flows through all the world's rivers combined. This massive movement of water carries enormous amounts of heat from the equator to the poles, moderating temperatures in both regions and helping to maintain Earth's overall temperature balance. The circulation system is remarkably stable, but it can change in response to climate conditions. During ice ages, changes in temperature and salinity patterns have altered ocean circulation, affecting how heat is distributed around the planet. These changes in ocean circulation have, in turn, influenced regional and global climate patterns, demonstrating how different components of Earth's climate system are interconnected. Above the oceans, clouds form another crucial component of Earth's temperature regulation system. Clouds affect our planet's energy balance in two competing ways. They reflect incoming solar radiation back to space, which cools the planet, but they also trap outgoing infrared radiation, which warms the planet. The net effect depends on the type, altitude, thickness, and location of the clouds. Low, thick clouds generally have a net cooling effect because they're very good at reflecting solar radiation while being less effective at trapping infrared radiation. High, thin clouds tend to have a net warming effect because they allow most solar radiation to pass through while efficiently trapping infrared radiation. The overall effect of Earth's cloud cover is a net cooling of about 20 watts per square meter, helping to prevent our planet from becoming too warm. Cloud formation itself is closely tied to temperature and water vapor content in the atmosphere. As air warms, it can hold more water vapor. But when this warm, moist air rises and cools, the water vapor condenses into tiny droplets that form clouds. Changes in temperature therefore affect cloud formation. which affects how much solar radiation is reflected back to space, which affects temperature. This creates complex feedback loops that scientists are still working to understand fully. The formation of clouds also depends on the presence of tiny particles in the atmosphere that serve as condensation nuclei. These particles can come from sea spray, dust, volcanic emissions, or biological sources. Changes in the availability of these particles can affect cloud formation and properties, adding another layer of complexity to Earth's temperature regulation system. On land, vegetation plays multiple roles in climate regulation. Plants absorb carbon dioxide from the atmosphere during photosynthesis, temporarily storing carbon in their tissues and releasing oxygen. When plants die and decompose, much of this carbon returns to the atmosphere, but some becomes incorporated into soils, where it can remain for decades or centuries. Forests and other vegetation also affect local and regional temperatures through their influence on the water cycle. Plants absorb water through their roots and release it through their leaves in a process called transpiration. This water evaporation has a cooling effect, similar to how sweating cools the human body. Large forests can significantly lower regional temperatures through this evapotranspiration process. The color and texture of different land surfaces also affect temperature regulation through their influence on albedo. Dark surfaces like forests and soil absorb more solar radiation than light-colored surfaces like grasslands or snow-covered areas. Changes in vegetation patterns therefore affect how much solar energy is absorbed by the land surface, which influences local and regional temperatures. Seasonal changes in vegetation create regular cycles in atmospheric carbon dioxide concentrations and surface properties that help regulate temperature over annual timescales. During spring and summer in the Northern Hemisphere, plant growth removes large amounts of carbon dioxide from the atmosphere, while increased leaf cover changes surface albedo and evapotranspiration rates. These seasonal cycles create predictable variations in Earth's energy balance that contribute to climate stability. The slow but constant process of rock weathering provides another temperature regulation mechanism that operates over much longer timescales. When rocks are exposed to water and carbon dioxide, chemical reactions gradually break down the minerals, consuming atmospheric carbon dioxide in the process. The products of these reactions are eventually carried to the oceans, where they contribute to the formation of carbonate sediments. This silicate weathering process becomes more active as temperatures rise because chemical reactions proceed faster in warmer conditions. This creates a negative feedback loop where warming leads to increased weathering, which removes more carbon dioxide from the atmosphere, ultimately cooling the planet. Conversely, during cooler periods, weathering slows down, allowing carbon dioxide to accumulate and providing warming. Recent research has confirmed that this stabilizing feedback mechanism has operated throughout Earth's history, helping to maintain habitable temperatures despite dramatic changes in solar radiation, volcanic activity, and other external forces. The timescale of this process, operating over hundreds of thousands of years, matches the duration of climate stability that scientists observe in the geological record. Volcanic activity adds another dimension to Earth's temperature regulation system, operating on intermediate timescales between weather and geological processes. Individual volcanic eruptions can affect global climate for several years by injecting particles and gases into the atmosphere. Large explosive eruptions can cool global temperatures by 1 to 2 degrees Celsius for 2 to 3 years by increasing the amount of solar radiation reflected back to space. But volcanic activity also releases carbon dioxide and other greenhouse gases into the atmosphere, providing a warming influence that operates over longer timescales. Over millions of years, the balance between volcanic carbon dioxide emissions and removal through weathering and other processes has helped maintain Earth's long-term climate stability. The movement of continents through plate tectonics affects climate regulation over the longest timescales of all. As continents drift across Earth's surface, they change patterns of ocean circulation, alter the distribution of land and sea, and affect global weathering rates. Mountain building associated with plate tectonics exposes fresh rock surfaces to weathering, while the arrangement of continents affects ocean currents and atmospheric circulation patterns. These geological processes operate so slowly that their effects are barely perceptible over human timescales, but they've played crucial roles in shaping Earth's climate over hundreds of millions of years. The current arrangement of continents, with a large ice sheet over Antarctica and an Arctic Ocean surrounded by land, contributes to our planet's current climate state and its sensitivity to other climate influences. Ice and snow add another layer of complexity to Earth's temperature regulation through their effects on albedo. Ice-covered surfaces reflect up to 90% of incoming solar radiation, while dark ocean water reflects only about 6%. This creates powerful feedback effects where changes in ice coverage can dramatically amplify temperature changes. When ice melts due to warming, it exposes darker surfaces that absorb more solar energy, leading to further warming and more ice melt. When ice expands during cooling, it increases Earth's overall reflectivity, reducing absorbed solar energy and promoting further cooling. This ice albedo feedback has played important roles in Earth's climate history, contributing to both ice ages and ice-free periods. The Arctic regions demonstrate these ice albedo feedbacks in particularly dramatic ways. Here, where temperatures are rising more rapidly than anywhere else on Earth, we can observe temperature regulation mechanisms responding to change in real time. Arctic sea ice, which once reflected most of the sun's energy back to space, has been retreating, exposing darker ocean water that absorbs far more heat. This creates what scientists call Arctic amplification, where the polar regions warm at rates several times faster than the global average. Yet even this dramatic change reveals the interconnected nature of Earth's regulatory systems. As Arctic ice retreats, it affects atmospheric circulation patterns far from the polar regions. The temperature difference between the Arctic and lower latitudes helps drive the jet stream and other large-scale wind patterns that distribute heat around the planet. Changes in this temperature gradient can alter weather patterns thousands of miles away, demonstrating how local changes in one part of Earth's regulatory system can influence climate conditions across the entire planet. The deep ocean provides another crucial component of Earth's temperature regulation, one that operates on timescales that dwarf human experience. The vast depths of our oceans contain waters that began their journey at the surface centuries ago, carrying with them the temperature and chemical signatures of past climates. These deep waters move through ocean basins at speeds measured in centimeters per year, creating a climate memory that extends back hundreds of generations. Radiocarbon dating of deep ocean water reveals that some of these waters last saw sunlight over 1,000 years ago. As they slowly circulate through the ocean depths, they carry heat, dissolved gases, and nutrients around the planet, creating connections between distant regions and different time periods. A cooling event in the North Atlantic centuries ago still influences water temperatures in the deep Pacific today, while current changes in polar regions will affect deep ocean conditions for many centuries to come. 2. This slow circulation acts as a vast thermal reservoir, absorbing heat during warm periods and releasing it during cool periods. The ocean's enormous capacity to store heat means that even dramatic changes in atmospheric conditions may take decades or centuries to fully penetrate to the deep ocean. This thermal inertia provides stability to Earth's climate system, buffering against rapid changes and helping to maintain the long-term conditions that life depends upon. The deep ocean also serves as an enormous reservoir for dissolved carbon dioxide, holding roughly 50 times more carbon than the atmosphere. Changes in deep ocean circulation can affect how much of this carbon remains dissolved and how much returns to the atmosphere, creating feedback loops that operate over centuries and millennia. During ice ages, changes in ocean circulation patterns helped regulate atmospheric carbon dioxide concentrations, contributing to the planet's transitions between glacial and warmer periods. Marine life adds another layer to ocean-based temperature regulation. Microscopic phytoplankton in the surface waters perform photosynthesis, much like land plants, removing carbon dioxide from the atmosphere and releasing oxygen. When these tiny organisms die, some sink to the ocean depths, carrying carbon away from the atmosphere for extended periods. Other marine organisms build shells and skeletons from dissolved carbon compounds, creating another pathway for removing atmospheric carbon dioxide. These biological processes respond to temperature changes in complex ways. Warmer waters can support different communities of marine organisms than cooler waters, and these different communities may have different effects on atmospheric composition. Some marine organisms also produce compounds that help seed cloud formation over the oceans, creating connections between marine biology and atmospheric processes that scientists are still working to understand fully. The seasonal rhythms of marine life create regular cycles in ocean chemistry and atmospheric composition. During spring and summer, increased sunlight promotes phytoplankton blooms that remove large amounts of carbon dioxide from the atmosphere. These seasonal biological pulses complement the seasonal changes in terrestrial vegetation, creating global rhythms in atmospheric composition that help regulate Earth's energy balance throughout the year. Permafrost regions in the Arctic and other high-latitude areas represent another component of Earth's temperature regulation system, one that demonstrates how different regulatory mechanisms can shift between stabilizing and destabilizing effects. These permanently frozen soils contain enormous amounts of organic matter that has accumulated over thousands of years. Under normal conditions, this frozen organic matter remains locked away, unable to decompose and release carbon to the atmosphere. But as temperatures warm, permafrost begins to thaw, allowing decomposition to begin. This process releases both carbon dioxide and methane to the atmosphere, adding to the greenhouse effect and causing more warming. The decomposition process itself generates heat, creating a feedback loop where thawing permafrost warms the soil, accelerating further thawing and decomposition. Yet even this potentially destabilizing process operates within the broader context of Earth's regulatory systems. The carbon released from thawing permafrost becomes available for uptake by growing vegetation in warming Arctic regions. Changes in vegetation patterns affect surface albedo and evapotranspiration rates, creating new feedback loops that may partially offset the warming effects of permafrost carbon release. High-latitude vegetation changes illustrate the complex nature of Earth's regulatory responses. As temperatures warm in Arctic regions, shrubs and trees can grow in areas previously dominated by grasses and mosses. This vegetation change decreases surface reflectivity during summer, as darker vegetation absorbs more solar energy than lighter-colored tundra. But the same vegetation changes can increase snow retention during winter, raising surface reflectivity during the season when solar energy is most limited. These competing effects demonstrate how Earth's regulatory systems often involve trade-offs between different mechanisms operating at different times or scales. The net effect of vegetation changes on temperature regulation depends on the specific types of vegetation involved, the timing of their growth cycles, and their interactions with snow cover, soil properties, and atmospheric conditions. Atmospheric chemistry provides another dimension to Earth's temperature regulation through the complex interactions between different gases and particles suspended in the air. Beyond the major greenhouse gases, our atmosphere contains trace amounts of many other compounds that affect the energy balance in subtle but important ways. Ozone in the upper atmosphere absorbs ultraviolet radiation from the sun, warming the stratosphere while protecting Earth's surface from harmful radiation. Ozone in the lower atmosphere acts as a greenhouse gas, contributing to surface warming. Aerosols, tiny particles suspended in the atmosphere, affect temperature regulation through their interactions with both radiation and cloud formation. Some aerosols reflect sunlight back to space, providing a cooling effect, while others absorb radiation and warm the atmosphere. Dark particles like soot can have warming effects when suspended in the atmosphere, but cooling effects when they settle on snow and ice surfaces by reducing their reflectivity. Many aerosols also serve as condensation nuclei for cloud droplets, affecting cloud formation and properties. Changes in aerosol concentrations can therefore affect cloud cover, cloud brightness, and precipitation patterns, creating indirect effects on temperature regulation that can be larger than their direct radiative effects. Natural sources of aerosols include sea spray, dust storms, volcanic emissions, and particles produced by vegetation and marine organisms. The atmosphere's chemical composition is constantly changing through the interactions between different compounds and their exposure to sunlight. These photochemical reactions create and destroy various gases and particles, maintaining a dynamic balance that affects Earth's energy balance. Some reactions are promoted by warmer temperatures, while others are inhibited, creating temperature-dependent feedback loops in atmospheric chemistry. Lightning provides another connection between atmospheric processes and temperature regulation. Lightning produces nitrogen compounds that can act as fertilizers when they reach the ground, affecting plant growth and carbon uptake. Lightning also produces ozone and other reactive compounds that affect atmospheric chemistry. The frequency and intensity of lightning depend on atmospheric temperature and humidity, creating feedback loops between temperature and atmospheric composition. Dust storms demonstrate another way that land surface conditions affect atmospheric properties and temperature regulation. When strong winds lift dust particles into the atmosphere, these particles can travel thousands of miles, affecting cloud formation and radiation balance far from their source regions. The frequency and intensity of dust storms depend on surface conditions, including soil moisture, vegetation cover, and temperature patterns. Some dust particles contain nutrients that fertilize marine and terrestrial ecosystems when they settle out of the atmosphere. Iron-rich dust from desert regions can stimulate phytoplankton growth in distant ocean areas, affecting marine carbon uptake and oxygen production. This creates connections between desert regions and marine ecosystems that operate through atmospheric transport processes. The water cycle connects all of these regulatory mechanisms through the movement of water between the atmosphere, land, and oceans. Water evaporated from ocean surfaces carries energy into the atmosphere, where it can be transported thousands of miles before condensing and releasing that energy as latent heat. This energy transport helps moderate temperature differences between different regions and between different seasons. Precipitation patterns affect vegetation growth, soil moisture, and surface reflectivity, influencing local and regional temperature regulation. Heavy precipitation can promote plant growth and increase evapotranspiration, providing cooling effects. Light precipitation, or drought, can stress vegetation and reduce evapotranspiration, potentially leading to warming. The timing of precipitation relative to growing seasons affects how efficiently ecosystems can regulate local temperatures through biological processes. Mountain ranges play special roles in the water cycle and temperature regulation by forcing air masses to rise and cool, promoting precipitation on their windward sides while creating drier conditions on their leeward sides. These orographic effects create regional climate patterns that persist over long periods, contributing to the stability of local and regional temperature regulation systems. Snowfall and snowmelt create seasonal cycles in surface reflectivity and water availability that affect temperature regulation over annual timescales. Snow cover reflects most incoming solar radiation, keeping surface temperatures cool even when solar radiation is strong. As snow melts, it exposes darker surfaces and provides water for plant growth, creating seasonal transitions in surface properties and biological activity. Glaciers and ice sheets represent long-term water storage systems that affect temperature regulation over decades to centuries. These ice masses grow during cool periods and shrink during warm periods, creating delayed responses to temperature changes that help stabilize climate over intermediate timescales. The slow response of ice masses to temperature changes means that they continue to affect climate long after the conditions that created them have changed. River systems transport water, sediments, and dissolved substances from land to ocean, connecting terrestrial and marine components of Earth's regulatory systems. Rivers carry weathering products from rock breakdown to the oceans, supporting the long-term carbon regulation system. They also transport nutrients that support marine ecosystems and organic matter that affects ocean chemistry. Wetlands provide important connections between terrestrial and aquatic systems, affecting both local and regional temperature regulation. These ecosystems can store large amounts of carbon in waterlogged soils where decomposition is slow. They also affect local humidity and temperature through evapotranspiration, often creating cooler, more stable microclimates than surrounding areas. The interconnections between all these regulatory mechanisms create a climate system that is both stable and dynamic, capable of maintaining habitable conditions while responding to changing external conditions. No single mechanism controls Earth's temperature. Instead, the interactions between multiple processes operating at different scales create emergent properties that regulate climate more effectively than any individual process could alone. These regulatory systems have maintained Earth's habitability through dramatic changes in external conditions over billions of years. Solar radiation has increased by roughly 30% since life first appeared on Earth. Yet global temperatures have remained within the narrow range that allows liquid water to exist. Massive volcanic events, asteroid impacts, and other catastrophic events have temporarily disrupted the climate system, but the regulatory mechanisms have consistently restored conditions suitable for life. The resilience of Earth's temperature regulation systems emerges from their redundancy and interconnectedness. When one regulatory mechanism is disrupted or overwhelmed, others can compensate, maintaining overall climate stability. The different timescales of various regulatory processes provide stability over short periods, while allowing adaptation to long-term changes in external conditions. Understanding these natural regulatory systems helps us appreciate both the robustness and the sensitivity of Earth's climate. The same mechanisms that have maintained habitability for billions of years continue to operate today, responding to both natural and human-induced changes in atmospheric composition, land use, and energy balance. The climate system's complexity means that predicting its exact responses to changing conditions remains challenging, but the fundamental regulatory processes continue to operate according to the same physical and chemical principles that have governed Earth's climate throughout its history. As we rest in the knowledge of these vast regulatory systems, we can find comfort in the understanding that Earth's temperature regulation emerges naturally from simple physical laws acting over deep time. The same gravitational forces that hold our planet in its orbit also drive ocean circulation and atmospheric pressure systems. The same electromagnetic radiation from our sun that warms our days also powers the photosynthesis that removes carbon dioxide from our atmosphere. The same chemical bonds that hold molecules together also drive the weathering reactions that slowly remove excess carbon from our atmosphere over geological time. These regulatory mechanisms require no consciousness or intention to operate. They arise naturally from the fundamental properties of matter and energy, creating a self-organizing system that maintains the conditions necessary for the complexity and beauty of life on Earth. In this understanding, we find not just scientific knowledge, but a deep sense of belonging to a planet whose very physics conspire to maintain the conditions that make our existence possible. The complexity of Earth's regulatory systems reveals itself most clearly when we examine how different processes interact across multiple timescales simultaneously. While some mechanisms respond to changes within hours or days, others require centuries or millennia to fully express their regulatory effects. This temporal layering creates a climate system with both immediate responsiveness and long-term stability, like a musical composition where different instruments play at different rhythms but harmonize to create a unified whole. Consider how a single raindrop illustrates these interconnected systems. That drop of water may have evaporated from a tropical ocean weeks ago, carrying with it the thermal energy of warm surface waters. As it rose into the atmosphere, it became part of a cloud system that reflected some solar radiation back to space, while trapping some infrared radiation from below. The energy released when that water vapor condensed into the raindrop helped drive atmospheric circulation patterns that transported heat from the tropics toward higher latitudes. When that raindrop falls to Earth, it may land on a forest canopy, where it will cool the leaves through evaporation and provide moisture for photosynthesis that removes carbon dioxide from the atmosphere. Or it may fall on exposed rock, where it will begin the slow process of chemical weathering that gradually draws atmospheric carbon into the oceans. Perhaps it will join a stream that carries dissolved minerals to the sea, or soak into soil where it will support the growth of plants that will store carbon for decades in their woody tissues. Each of these pathways connects that single raindrop to different aspects of Earth's temperature regulation system, operating on timescales from minutes to millennia. The immediate cooling effect of evaporation operates within seconds. The photosynthesis it enables removes carbon from the atmosphere over the course of a growing season. The weathering reactions it participates in may continue for thousands of years. The ocean circulation it eventually joins may carry its influence around the globe over the course of centuries. This multi-scale integration extends throughout Earth's regulatory systems. The daily cycle of solar heating and radiative cooling creates temperature rhythms that drive local wind patterns and evaporation rates. These daily rhythms aggregate into seasonal patterns that influence vegetation growth cycles and atmospheric composition. The seasonal patterns, in turn, create annual averages that reflect longer-term climate conditions shaped by ocean circulation, ice sheet dynamics, and atmospheric chemistry. Decades of seasonal cycles reveal the influence of even slower processes, like changes in ocean circulation patterns or gradual shifts in atmospheric composition. Centuries of climate records show the effects of solar variability, volcanic activity, and other external influences. Millennia of geological evidence reveal the operation of Earth's slowest regulatory mechanisms, including the weathering processes that stabilize atmospheric composition over hundreds of thousands of years. The atmosphere itself demonstrates this temporal complexity beautifully. At any given moment, our atmosphere contains water vapor that evaporated from the ocean surface just hours ago, alongside carbon dioxide molecules that may have been cycling through the atmosphere, oceans, and biosphere for centuries. Oxygen molecules produced by photosynthesis last year mix with oxygen that may have been released from water molecules broken apart in the upper atmosphere decades ago. Some atmospheric components have residence times measured in days, like water vapor that quickly condenses and falls as precipitation. Others persist for years, like the aerosols produced by major volcanic eruptions that can influence global temperatures for several seasons. Carbon dioxide molecules typically spend several years in the atmosphere before being absorbed by plants or dissolved in seawater, while some trace gases may persist for decades or centuries before being broken down by chemical reactions. This atmospheric mixing creates a dynamic system where recent changes interact with the accumulated effects of past processes. The greenhouse effect we experience today results from greenhouse gases emitted over many years, while the photosynthesis occurring today will influence atmospheric composition for years to come. Changes in one component of the system propagate through these different timescales, creating complex response patterns that may not become fully apparent for years or decades. Ocean systems demonstrate even longer timescales of integration and response. Surface waters that absorb heat and carbon dioxide today will carry that thermal and chemical signature with them as they gradually mix into deeper layers. Some of this surface water will remain near the surface for months or years, continuing to exchange heat and gases with the atmosphere, but some will be carried into the deep ocean circulation system, where it may remain isolated from the atmosphere for centuries. This means that changes in surface conditions today will continue to influence deep ocean properties for hundreds of years into the future. Conversely, the deep waters that rise to the surface today carry with them the thermal and chemical conditions from centuries past. The deep ocean thus serves as a vast archive of past climate conditions, while simultaneously influencing current and future climate through its slow circulation and massive heat capacity. The gradual mixing between surface and deep waters creates climate responses that unfold over multiple timescales. Immediate changes in surface temperature may be partially buffered by heat exchange with the upper ocean over months to years. But the full response of the ocean system, including changes in deep circulation patterns and deep water properties, may require decades to centuries to fully develop. This ocean inertia provides crucial stability to Earth's climate system. Rapid changes in atmospheric conditions cannot immediately alter the enormous thermal reservoir of the deep ocean, which helps prevent extreme climate swings. But this same inertia means that once changes begin to penetrate the deep ocean system, they persist for very long periods, creating climate commitments that extend far beyond the original forcing. Marine ecosystems add another layer of complexity to these ocean-based regulatory mechanisms. Phytoplankton communities respond to changes in temperature, nutrients, and light conditions over seasonal and annual cycles. These responses affect both the biological pump that removes carbon from surface waters and the production of compounds that influence cloud formation over the oceans. Different species of marine organisms have different optimal temperature ranges and different effects on ocean chemistry. As ocean temperatures change, the composition of marine communities shifts, potentially altering the ocean's role in carbon cycling and climate regulation. These biological responses operate on timescales of years to decades, creating delayed feedback loops between climate change and marine ecosystem function. Coral reefs exemplify these biological climate connections. These diverse ecosystems build massive carbonate structures that remove carbon from seawater, potentially affecting ocean chemistry and atmospheric carbon dioxide levels. The reef-building process requires specific temperature and chemistry conditions, making coral ecosystems sensitive indicators of ocean climate conditions. When ocean temperatures or acidity levels exceed coral tolerance limits, these ecosystems can shift rapidly from carbon removal to carbon release as coral organisms die and their carbonate structures begin to dissolve. These ecosystem shifts create additional feedback loops in the climate system, where changes in ocean conditions lead to changes in biological processes that further alter ocean chemistry and atmospheric composition. Terrestrial ecosystems display similar multi-timescale responses to climate conditions. Individual plants respond to temperature and moisture conditions over daily and seasonal cycles through changes in photosynthesis, respiration, and water use. These immediate responses affect local energy and water balances, influencing regional temperature and humidity patterns. Over longer timescales, plant communities respond to climate conditions through changes in species composition, growth rates, and geographic distributions. Forests may expand into previously unsuitable areas or retreat from areas that have become too warm or dry. Grasslands may shift between different dominant species with different effects on soil carbon storage and surface reflectivity. These vegetation changes create feedback loops with climate through their effects on surface properties and atmospheric composition. The expansion of forests into previously open areas decreases surface reflectivity and increases evapotranspiration, generally providing cooling effects. The conversion of forests to grasslands or bare soil has the opposite effects, generally promoting warming through increased surface reflectivity and decreased evapotranspiration. Soil systems integrate these vegetation responses over even longer timescales. Soils develop over centuries to millennia through the gradual accumulation of organic matter from plant and animal residues. Different vegetation types produce different amounts and types of organic matter, leading to different soil properties and carbon storage capacities. Soil organic matter represents one of Earth's largest carbon reservoirs, holding more carbon than the atmosphere and vegetation combined. Changes in climate conditions that affect plant productivity and decomposition rates can therefore have large impacts on atmospheric carbon dioxide concentrations over decades to centuries. Warmer temperatures generally increase both plant productivity and decomposition rates, but these processes respond differently to temperature changes. In some ecosystems, increased decomposition may release more carbon from soils than increased plant growth can absorb, creating a net source of atmospheric carbon dioxide. In other ecosystems, enhanced plant growth may more than compensate for increased decomposition, creating a net carbon sink. These soil-climate interactions demonstrate how Earth's regulatory systems can shift between stabilizing and destabilizing effects depending on the specific conditions and the magnitude of changes involved. Small climate changes may enhance soil carbon storage and provide negative feedback to climate change. But larger changes may overwhelm this regulatory capacity and convert soil carbon reservoirs into sources of additional greenhouse gases. Fire represents another important connection between terrestrial ecosystems and climate regulation. Natural fire cycles have shaped many ecosystems for millions of years, creating patterns of vegetation growth, death, and regeneration that affect carbon storage and surface properties. Fire frequency and intensity depend on climate conditions, including temperature, precipitation, and humidity patterns. Climate changes that increase fire frequency or intensity can rapidly convert stored carbon in vegetation and soils back to atmospheric carbon dioxide. Large fire years can release amounts of carbon comparable to entire countries' fossil fuel emissions, demonstrating how ecosystem processes can create significant climate feedbacks. Yet fire also plays important roles in ecosystem function and long-term carbon cycling. Many plant species have evolved adaptations to periodic fires, and some ecosystems require fire to maintain their structure and diversity. Fire clears accumulated dead plant material and returns nutrients to soils, often promoting new plant growth that can absorb atmospheric carbon dioxide. The net climate effects of fire depend on the balance between immediate carbon emissions and longer-term carbon uptake by recovering ecosystems. In ecosystems adapted to frequent low-intensity fires, this balance may favor long-term carbon storage. In ecosystems experiencing unusually large or frequent fires due to climate change, the balance may shift toward net carbon emissions. Mountain ecosystems demonstrate particularly complex interactions between climate and ecosystem function because of their steep gradients in temperature, precipitation, and growing conditions. As climate conditions change, the elevation zones suitable for different vegetation types shift upward or downward along mountain slopes. These vegetation zone shifts can occur relatively rapidly compared to other ecosystem changes, because plants can colonize suitable habitats within years or decades rather than centuries or millennia. Mountain ecosystems thus provide sensitive indicators of climate change and important insights into how ecosystem-climate interactions may evolve in the future. The upper elevations of mountain ranges also play important roles in regional water cycles through their effects on precipitation patterns and snowpack accumulation. Mountain snowpack serves as natural water storage, accumulating during winter and gradually melting during spring and summer to provide water for lower elevation ecosystems and human communities. Changes in mountain climate conditions affect both the amount of snow that accumulates and the timing of snowmelt, with cascading effects on regional water availability and ecosystem function. Earlier, snowmelt can shift the timing of peak water availability, potentially creating mismatches between water availability and the growing season needs of plants and animals. Glacial systems in mountain and polar regions represent another important component of Earth's temperature regulation that operates over intermediate timescales. Glaciers grow during periods of cool temperatures and high snowfall, and shrink during periods of warm temperatures or low snowfall. These changes in glacier size affect regional water supplies, sea levels, and surface reflectivity. The response time of glaciers to climate changes varies dramatically with glacier size and characteristics. Small mountain glaciers may respond to climate changes within years to decades, while large ice sheets require centuries to millennia to fully adjust to new climate conditions. This range of response times means that glacier systems provide information about climate changes across multiple timescales. Glacial ice also preserves a detailed record of past climate conditions through the accumulation of annual layers of snow and ice. Ice cores extracted from glaciers and ice sheets contain information about past temperatures, precipitation patterns, atmospheric composition, and volcanic activity, extending back hundreds of thousands of years. This glacial climate archive reveals that Earth's regulatory systems have maintained habitable conditions through a wide range of natural climate variations. Ice age cycles, volcanic eruptions, solar variability, and other natural climate influences have all been accommodated within the range of conditions that support complex life and diverse ecosystems. The ice core record also shows that Earth's climate system can transition between different stable states relatively rapidly when external conditions change sufficiently. These transitions demonstrate that Earth's regulatory systems, while generally stabilizing, can sometimes amplify changes rather than dampening them, leading to rapid shifts between different climate regimes. Desert ecosystems illustrate another set of climate ecosystem interactions that operate through different mechanisms than forest or grassland systems. Desert plants have evolved various strategies for surviving in hot, dry conditions, including specialized water storage tissues, reduced leaf surfaces, and dormancy during unfavorable periods. These adaptations allow desert ecosystems to persist under climate conditions that would be fatal to most other vegetation types, but they also mean that desert ecosystems may be less responsive to moderate climate changes than ecosystems in more favorable environments. Desert vegetation may not increase significantly, even if temperatures or precipitation increase moderately. However, desert ecosystems can contribute to regional and global climate regulation through their effects on dust emissions and surface reflectivity. Desert soils often have light colors that reflect significant amounts of solar radiation, helping to keep surface temperatures from becoming even more extreme. When vegetation cover increases in desert areas, it may actually decrease surface reflectivity and contribute to local warming. Dust emissions from desert regions affect climate regulation over much larger areas through their transport in the atmosphere. Desert dust can travel thousands of miles from its source, affecting cloud formation, precipitation patterns, and ocean productivity in distant regions. Iron-rich dust from some desert regions provides essential nutrients for marine phytoplankton in parts of the ocean where these nutrients are otherwise scarce. These long-distance connections created by atmospheric dust transport demonstrate how local ecosystem conditions can influence global climate regulation. Changes in desert vegetation, cover, or soil stability can affect dust emissions, which can then influence marine ecosystems and atmospheric processes in distant parts of the world. Wetland ecosystems provide another important set of climate ecosystem interactions, particularly through their effects on methane emissions and regional water cycles. Wetlands are among the most productive ecosystems on Earth, supporting high levels of plant and animal diversity while storing large amounts of carbon in waterlogged soils. The waterlogged conditions in wetlands slow decomposition of organic matter, allowing carbon to accumulate in soils over long periods. But these same conditions also promote the production of methane, a potent greenhouse gas, through anaerobic decomposition processes. Wetlands are responsible for a significant fraction of global methane emissions, creating a complex relationship between wetland ecosystem function and climate regulation. Changes in climate conditions that affect wetland water levels can dramatically alter these methane emissions. Drier conditions may reduce methane production, but increase carbon dioxide emissions as previously waterlogged soils become exposed to oxygen and decompose more rapidly. Wetter conditions may increase methane emissions while preserving soil carbon storage. Wetlands also play important roles in regional climate regulation through their effects on local humidity and temperature. Large wetland areas can moderate regional temperatures through evapotranspiration, creating cooler, more humid microclimates than surrounding upland areas. These effects can influence regional precipitation patterns and atmospheric circulation. Coastal ecosystems represent particularly important connections between terrestrial and marine climate regulation systems. Salt marshes, mangrove forests, and other coastal wetlands are among the most carbon-rich ecosystems on Earth, storing large amounts of carbon in both their vegetation and their soils. These ecosystems are also highly sensitive to sea level changes and storm activity, both of which are influenced by global climate conditions. Rising sea levels can inundate coastal ecosystems, potentially converting carbon sinks into carbon sources as stored organic matter decomposes under changed conditions. But coastal ecosystems also demonstrate remarkable resilience and adaptability. Many coastal plant species can migrate inland or adjust their growth patterns in response to changing water levels. Some coastal ecosystems may actually benefit from moderate increases in temperature or precipitation, potentially increasing their carbon storage capacity. The boundary zones between different ecosystem types often display particularly complex climate interactions. These ecotones, as scientists call them, typically experience environmental conditions that are intermediate between the adjacent ecosystem types, creating unique communities of plants and animals adapted to these transitional conditions. Climate changes can cause these boundary zones to shift, potentially altering the geographic distribution of different ecosystem types. Forest grassland boundaries may shift in response to changes in precipitation or fire frequency. Arctic tundra forest boundaries may shift in response to temperature changes. These ecosystem boundary shifts can have regional climate effects through their influence on surface properties and carbon cycling. The shifting of ecosystem boundaries also affects biodiversity patterns and wildlife habitat availability. Species adapted to particular ecosystem types may need to migrate to track suitable habitat as climate conditions change. Species adapted to boundary zones may find their habitat either expanding or contracting, depending on how climate changes affect the sharpness or location of ecosystem transitions. Urban and agricultural areas represent human-modified ecosystems that also interact with climate regulation systems in complex ways. Cities create urban heat islands through their concentration of heat-absorbing surfaces and waste heat production, but they can also influence regional climate through their effects on atmospheric circulation and precipitation patterns. Agricultural systems affect climate regulation through their influence on carbon cycling, surface reflectivity, and evapotranspiration rates. Different crops have different effects on these processes, and agricultural management practices can significantly influence the climate impacts of farming systems. The integration of all these ecosystem-climate interactions creates emergent properties in Earth's regulatory systems that arise from the complex web of connections between different components. No single ecosystem or region controls global climate, but the collective effects of ecosystem processes around the world create significant influences on atmospheric composition and energy balance. These emergent properties include the stability of atmospheric composition, despite constant exchanges of gases between the atmosphere and ecosystems. They include the maintenance of regional climate patterns, despite year-to-year variations in weather conditions. They include the capacity of the Earth system to accommodate moderate changes in external conditions while maintaining overall habitability. The redundancy built into these ecosystem-climate interactions provides resilience to Earth's regulatory systems. If climate changes disrupt ecosystem function in one region, ecosystem processes in other regions may compensate, maintaining overall global regulation. If one type of ecosystem becomes less effective at climate regulation, other ecosystem types may become more important. This redundancy emerges naturally from the diversity of Earth's ecosystems and the multiple pathways through which biological processes influence climate. The same climate regulation functions are performed by different organisms in different environments, using different biochemical pathways and operating at different scales. Forest ecosystems in tropical, temperate, and boreal regions all contribute to carbon cycling and climate regulation, but through different mechanisms and with different sensitivities to climate change. Marine ecosystems in different ocean basins all contribute to oceanic carbon cycling, but with different species compositions and different responses to temperature and chemistry changes. Grassland ecosystems on different continents all contribute to soil carbon storage and surface energy balance, but with different plant species and different relationships to fire and grazing. Desert ecosystems in different regions all contribute to regional energy balance and atmospheric dust loading, but with different soil types and different vegetation adaptations. This global diversity of ecosystem types and climate regulation mechanisms has evolved over hundreds of millions of years of Earth history. The current configuration represents the outcome of countless evolutionary innovations and ecosystem developments that have shaped how biological processes interact with physical and chemical climate regulation mechanisms. The fossil record reveals that Earth's ecosystems have undergone dramatic changes throughout geological history, including mass extinction events that eliminated large fractions of existing species. Yet Earth's overall capacity for climate regulation has persisted through these biological crises, suggesting that the fundamental mechanisms of ecosystem climate interaction are robust to even severe disruptions. New types of organisms have repeatedly evolved to fill ecological roles left vacant by extinction events. New ecosystem types have developed as continents drifted to new positions and climate conditions changed. The specific organisms and ecosystems involved in climate regulation have changed dramatically over Earth's history, but the overall regulatory capacity has been maintained. This evolutionary perspective on climate regulation suggests that Earth's regulatory systems have an inherent capacity for adaptation and reorganization in response to changing conditions. The mechanisms of climate regulation are not fixed, but rather represent dynamic processes that can evolve and adapt as conditions change. Understanding these adaptive capacities provides both reassurance about the long-term stability of Earth's climate regulation and insight into how these systems might respond to current and future changes. The same evolutionary processes that have maintained climate regulation throughout Earth's history continue to operate today, potentially generating new solutions to emerging climate challenges. The timescales involved in evolutionary adaptation, however, are typically much longer than the timescales of current climate changes. Evolutionary responses to changing climate conditions typically require generations to centuries, while current climate changes are occurring over decades. This mismatch in timescales means that evolutionary adaptation may not be able to maintain ecosystem climate regulation functions if changes occur too rapidly. Nevertheless, many organisms and ecosystems display remarkable phenotypic plasticity, allowing them to adjust their function and behavior in response to changing conditions without requiring genetic changes. These plastic responses can occur within individual lifetimes and may help maintain ecosystem climate regulation functions even during periods of rapid climate change. Plants may adjust their photosynthesis and water use patterns in response to changing temperature and atmospheric composition. Marine organisms may adjust their shell building and reproduction timing in response to changing ocean chemistry and temperature. Soil microbial communities may adjust their decomposition activities in response to changing temperature and moisture conditions. These plastic responses represent another layer of Earth's regulatory systems, providing short-term adaptive capacity that bridges between the immediate responses of physical and chemical processes and the longer-term responses of evolutionary change. This adaptive capacity emerges from the inherent variability and flexibility of biological systems, which have evolved in a world where environmental conditions are constantly changing. The integration of physical, chemical, biological, and evolutionary processes creates a climate regulation system that operates simultaneously across multiple timescales and spatial scales. Immediate responses to changing conditions occur within hours to days through physical and physiological processes. Intermediate responses occur over years to decades through ecosystem changes and population adjustments. Long-term responses occur over centuries to millennia through evolutionary adaptation and geological processes. This multi-scale integration provides Earth's climate regulation system with both stability and flexibility. The immediate responses provide rapid feedback that prevents small changes from growing into large disruptions. The intermediate responses provide adjustment mechanisms that accommodate moderate changes in external conditions. The long-term responses provide adaptive capacity that allows the system to evolve new regulatory mechanisms as conditions change. The overall result is a planet whose regulatory systems have maintained habitable conditions for billions of years while accommodating enormous changes in solar radiation, atmospheric composition, continental configuration, and biological evolution. These regulatory systems continue to operate today according to the same fundamental principles that have governed Earth's climate throughout its history. As we contemplate these vast interconnected systems, we can find deep comfort in their persistence and reliability. The regulatory mechanisms that maintain Earth's habitability arise naturally from the fundamental properties of matter and energy, requiring no external guidance or intervention to operate. They represent the spontaneous emergence of order and stability from the complex interactions of countless individual processes, each following simple physical and chemical laws. The carbon atoms cycling through our atmosphere today have participated in these regulatory processes for millions of years, moving through rocks and oceans, plants and animals, maintaining the chemical balance that makes life possible. The water molecules in our oceans have circulated through the global system countless times, carrying heat and dissolved substances around the planet, moderating temperatures and supporting the chemistry of life. The energy that drives these processes comes ultimately from our sun, the same star that has warmed our planet for billions of years, and will continue to do so for billions more. This solar energy, transformed and redistributed through Earth's regulatory systems, creates the stable conditions within which all the complexity and beauty of life can flourish. In this understanding, we find not just scientific knowledge, but a profound sense of belonging to a universe whose fundamental laws create the conditions for stability, complexity, and wonder. Earth's temperature regulation emerges naturally from these universal principles, creating a home whose very physics conspire to maintain the extraordinary phenomenon we call life. The story of how our planet maintains its temperature unfolds across timescales so vast that human minds can barely comprehend them, yet it operates through principles so elegant that we can find deep peace in their simplicity. Each component of this regulatory system follows the basic laws of physics and chemistry, creating patterns of stability that have persisted for billions of years through the most dramatic changes our planet has ever experienced. When we observe how heat moves through our climate system, we witness one of nature's most beautiful demonstrations of equilibrium in action. Heat always flows from warmer areas to cooler ones, following gradients of temperature with the same reliability that water flows downhill. In our atmosphere, this principle creates the gentle circulation patterns that distribute warmth from the sun-heated tropics toward the cooler polar regions, moderating temperatures across the entire planet. The atmosphere itself moves in response to these temperature differences through convection, the same process that causes warm air to rise from a heated surface. As solar energy warms the ground and oceans near the equator, the heated air becomes less dense and rises high into the atmosphere. This rising air creates space for cooler air to flow in from surrounding areas, establishing circulation patterns that operate continuously, day and night, season after season, year after year. These atmospheric circulation patterns create the trade winds, the westerlies, and the polar easterlies that sailors and weather forecasters know so well. But they also create something more profound, a global system for redistributing heat that prevents any region from becoming too hot or too cold for extended periods. The same physical principles that govern the movement of air in a heated room govern the movement of our entire atmosphere, scaled up to planetary proportions but operating according to identical laws. Water vapor plays a particularly elegant role in this atmospheric heat distribution system. When water evaporates from warm ocean surfaces, it absorbs energy in the process, cooling the surface slightly. This water vapor rises with the warming air, carrying its absorbed energy high into the atmosphere. When the water vapor eventually condenses back into liquid droplets to form clouds and precipitation, it releases that stored energy, warming the surrounding air at higher altitudes. This process, known as latent heat transport, moves enormous amounts of energy from Earth's surface into the upper atmosphere, where it can be radiated away to space more efficiently. It's a natural air conditioning system that operates continuously wherever water evaporates and condenses, providing cooling where energy is abundant and warming where energy is needed for atmospheric circulation. The formation of clouds through this condensation process creates one of Earth's most dynamic regulatory mechanisms. Each tiny cloud droplet forms around microscopic particles suspended in the atmosphere, particles that might have originated from sea spray, dust storms, volcanic eruptions, or even the metabolic processes of marine organisms. These cloud condensation nuclei demonstrate how even the smallest components of our planet's systems contribute to climate regulation. Once formed, clouds interact with radiation in complex ways that vary depending on their altitude, thickness, and composition. The ice crystals in high cirrus clouds interact differently with radiation than the water droplets in low stratus clouds. Towering cumulus clouds that extend through multiple atmospheric layers create different radiative effects at different altitudes within the same cloud system. This diversity of cloud types and properties creates a regulatory system that responds differently to different atmospheric conditions. During periods when the lower atmosphere is warming rapidly, increased evaporation tends to produce more low, thick clouds that reflect additional sunlight back to space, providing a cooling influence. During periods when the upper atmosphere is cooling, changes in atmospheric circulation may favor the formation of high, thin clouds that trap more infrared radiation, providing a warming influence. The water cycle that drives cloud formation operates as a vast distillation system, continuously purifying and redistributing water around the planet. Solar energy provides the power for this distillation, evaporating water from the oceans and leaving behind salt and other dissolved substances. The purified water vapor travels through the atmosphere before condensing and falling as precipitation, which gradually makes its way back to the oceans through rivers and groundwater flow. This cycle moves approximately 500,000 cubic kilometers of water through the atmosphere every year, an amount equivalent to a layer about 40 centimeters deep covering the entire planet's surface. The energy required to evaporate this much water and the energy released when it condenses represents one of the largest energy fluxes in Earth's climate system, comparable to the total energy consumption of human civilization multiplied by several thousand. Rivers play crucial roles in this water cycle, beyond simply returning precipitation to the oceans. As water flows across the landscape, it participates in chemical weathering reactions that gradually break down rock minerals and transport the products to the sea. These weathering reactions consume atmospheric carbon dioxide, providing one of the most important long-term climate regulation mechanisms on our planet. The process begins when carbon dioxide from the atmosphere dissolves in rainwater, forming weak carbonic acid. This slightly acidic water reacts with silicate minerals in rocks, gradually dissolving them and releasing various elements into solution. Some of these dissolved substances, particularly calcium and magnesium, eventually reach the oceans where they combine with dissolved carbon dioxide to form carbonate minerals that settle to the sea floor. This silicate weathering process operates as a global thermostat over geological timescales. When global temperatures rise, chemical reaction rates increase, accelerating the weathering process and removing more carbon dioxide from the atmosphere. When global temperatures fall, weathering slows down, allowing carbon dioxide to accumulate in the atmosphere. The feedback loop is self-regulating, providing stability over hundreds of thousands of years. Mountain ranges play special roles in both weathering and climate regulation through their effects on atmospheric circulation and precipitation patterns. When air masses encounter mountain barriers, they are forced to rise and cool, often producing enhanced precipitation on the windward slopes while creating drier conditions on the leeward sides. This orographic effect creates stable regional climate patterns that persist as long as the mountains remain in place. The weathering of mountain rocks proceeds more rapidly than the weathering of rocks in flat terrain because steep slopes constantly expose fresh rock surfaces through erosion and mass wasting. Mountain ranges therefore act as particularly active sites for the chemical weathering reactions that regulate atmospheric carbon dioxide over long timescales. The uplift of new mountain ranges through tectonic processes has historically coincided with periods of global cooling, as enhanced weathering removes excess carbon dioxide from the atmosphere. Volcanic activity provides a counterbalance to this carbon dioxide removal through weathering by returning carbon from Earth's interior to the atmosphere. When magma rises from the deep Earth and erupts at the surface, it releases carbon dioxide that has been stored in rocks for millions of years. This volcanic carbon dioxide emission represents a crucial component of the long-term carbon cycle, preventing the weathering process from gradually removing all carbon dioxide from the atmosphere. The balance between volcanic carbon dioxide emissions and removal through weathering has maintained atmospheric carbon dioxide concentrations within the range necessary for liquid water throughout most of Earth's history. During periods when volcanic activity was particularly intense, atmospheric carbon dioxide concentrations rose, leading to warmer global temperatures. During periods when volcanic activity was reduced while weathering continued, atmospheric carbon dioxide concentrations fell, leading to cooler global temperatures. Individual volcanic eruptions can also affect climate over shorter timescales through their emission of sulfur compounds and fine particles into the atmosphere. Large, explosive eruptions inject these materials high into the stratosphere, where they form tiny droplets of sulfuric acid that remain suspended for several years. These stratospheric aerosols reflect additional sunlight back to space, causing measurable cooling of global temperatures for 2 to 3 years after major eruptions. The 1815 eruption of Mount Tambora in Indonesia provides a well-documented example of this volcanic climate influence. The eruption injected so much material into the stratosphere that it caused noticeable cooling throughout the northern hemisphere, leading to crop failures and what became known as the year without a summer in 1816. Yet even this dramatic climate impact was temporary, demonstrating the atmosphere's ability to gradually clear volcanic debris and return to pre-eruption conditions. Plate tectonic processes operate over much longer timescales, but create equally important influences on Earth's climate regulation system. As continents drift across Earth's surface, they alter patterns of ocean circulation, change the distribution of land and sea, and affect global weathering rates. The current arrangement of continents, with the large land masses at high latitudes in both hemispheres, contributes to our planet's capacity to support extensive ice sheets and experience ice age cycles. Ocean basin geometry, controlled by plate tectonics, determines how ocean currents can flow between different regions. The opening or closing of oceanic gateways through continental drift can dramatically alter global ocean circulation patterns, affecting how heat is distributed between different ocean basins and between different latitudes. The opening of Drake Passage between South America and Antarctica, for example, allowed the formation of the Antarctic Circumpolar Current that now isolates Antarctica from warmer waters and helps maintain its ice sheet. The slow collision of continents through plate tectonics creates mountain ranges that affect both regional and global climate patterns. The ongoing collision between India and Asia that has created the Himalayan mountain range has influenced monsoon patterns across much of Asia, while also enhancing global weathering rates through the exposure of fresh rock surfaces at high altitudes. These tectonic climate influences unfold over millions of years, creating the geological context within which shorter-term climate variations occur. Seafloor spreading and subduction, the fundamental processes of plate tectonics, also affect the long-term carbon cycle by controlling the rate at which carbon-bearing rocks are recycled through Earth's interior. When oceanic plates carrying carbonate sediments are subducted into the mantle, they carry carbon into Earth's interior, where it may eventually be returned to the atmosphere through volcanic eruptions. The rate of this tectonic carbon recycling affects the long-term balance between carbon storage in rocks and carbon content in the atmosphere. The magnetic field generated by Earth's molten iron core provides another form of planetary regulation that operates over geological timescales. This magnetic field deflects most of the charged particles streaming from the Sun as the solar wind, preventing them from stripping away our atmosphere, as has happened on Mars. The magnetic field also helps protect the ozone layer in our upper atmosphere from solar radiation, maintaining the atmospheric chemistry that supports life at Earth's surface. Changes in the strength and orientation of Earth's magnetic field over geological time have been recorded in the magnetic signatures of ancient rocks. These records show that the magnetic field has varied significantly throughout Earth's history, occasionally even reversing polarity completely. Yet despite these variations, the magnetic field has provided continuous protection for our atmosphere and climate system, contributing to the long-term stability that has allowed complex life to evolve. Earth's rotation provides another fundamental influence on climate regulation through its effects on atmospheric and oceanic circulation patterns. The Coriolis effect, caused by Earth's rotation, deflects moving air and water masses, creating the spiral patterns we observe in weather systems and ocean currents. This rotation-induced deflection helps organize atmospheric and oceanic circulation into stable patterns that efficiently distribute heat between different latitudes. The length of Earth's day has gradually increased throughout geological history as tidal friction slowly transfers angular momentum from Earth's rotation to the Moon's orbital motion. This very gradual slowing of Earth's rotation has subtle effects on atmospheric circulation patterns and tidal mixing in the oceans. Yet these changes occur so slowly that they do not disrupt the fundamental regulatory mechanisms that maintain climate stability. The Moon itself plays important roles in Earth's climate regulation through its gravitational effects on ocean tides and Earth's axial tilt. Ocean tides mix surface and deeper waters, affecting both heat transport and the cycling of nutrients and dissolved gases. This tidal mixing helps maintain the ocean circulation patterns that distribute heat around the globe and supports the marine ecosystems that participate in climate regulation. The Moon's gravitational influence also helps stabilize Earth's axial tilt, preventing the dramatic changes in seasonal patterns that would occur if our planet's rotation axis wandered freely. Mars, which lacks a large moon, experiences much larger variations in axial tilt over geological time, leading to extreme climate changes as polar regions alternately point toward or away from the Sun. Earth's stable axial tilt, maintained by lunar gravity, provides the consistent seasonal patterns that have allowed life to adapt and evolve in predictable environmental cycles. Solar radiation itself varies over multiple timescales, creating external influences on Earth's climate regulation system. The Sun's energy output varies slightly with the 11-year solar cycle, changes more significantly over longer periods as the Sun evolves, and exhibits occasional dramatic events like solar flares that can affect Earth's upper atmosphere. Yet Earth's regulatory systems have accommodated all of these solar variations while maintaining habitable conditions. The gradual increase in solar luminosity over geological time represents one of the most remarkable demonstrations of Earth's regulatory capacity. When life first evolved over 3 billion years ago, the Sun was approximately 25 to 30% fainter than it is today. Without Earth's regulatory mechanisms, this increase in solar energy would have caused a dramatic warming that would have boiled away the oceans and sterilized the planet. Instead, atmospheric composition has changed in ways that have largely compensated for increasing solar luminosity, maintaining global temperatures within the range suitable for liquid water throughout most of Earth's history. Early in Earth's history, when the Sun was fainter, higher concentrations of greenhouse gases kept the planet warm enough for life. As the Sun gradually brightened, biological and geological processes gradually reduced atmospheric greenhouse gas concentrations, preventing runaway warming. This long-term regulation of atmospheric composition demonstrates the remarkable stability that emerges from the interactions between multiple regulatory mechanisms operating over different timescales. No single process could have maintained habitable conditions through such a large change in external energy input. but the combined effects of biological evolution, continental drift, volcanic activity, weathering, and ocean circulation have collectively adjusted Earth's energy balance to accommodate the changing sun. The ice ages of the past few million years provide another compelling example of Earth's regulatory systems in operation over intermediate timescales. These dramatic climate cycles, driven by changes in Earth's orbital parameters, demonstrate how astronomical forcing interacts with Earth's internal regulatory mechanisms to produce complex climate responses. Changes in the eccentricity of Earth's orbit, the obliquity of its rotational axis, and the precession of its orbital orientation create cyclical variations in the seasonal and latitudinal distribution of solar radiation. These Milankovitch cycles provide the pacing for ice age rhythms, but the magnitude of climate change during ice ages is much larger than would be expected from the orbital forcing alone. The ice albedo feedback mechanism amplifies the orbital forcing by creating self-reinforcing cycles of cooling and warming. When orbital conditions favor cooling in northern regions where large ice sheets can form, the growing ice increases Earth's reflectivity, causing additional cooling that promotes further ice growth. When orbital conditions shift to favor warming, ice sheets begin to retreat, exposing darker surfaces that absorb more solar radiation and accelerate the warming. Ocean circulation changes during ice ages provide additional amplification of the orbital forcing through their effects on carbon dioxide cycling and heat transport. During glacial periods, changes in ocean circulation patterns affect the exchange of carbon dioxide between the deep ocean and the atmosphere, contributing to the lower atmospheric carbon dioxide concentrations observed during ice ages. These circulation changes also affect the distribution of heat between different ocean basins, influencing regional climate patterns around the world. The regular cycling between glacial and interglacial conditions demonstrates that Earth's climate system can exist in multiple stable states, with transitions between these states triggered by relatively small external changes but amplified by internal feedback mechanisms. The current interglacial period, which began about 11,000 years ago, represents one of these stable states, maintained by the same regulatory mechanisms that have operated throughout the Ice Age cycles. Dust plays subtle but important roles in climate regulation through its effects on atmospheric radiation, cloud formation, and marine ecosystems. Desert regions produce enormous quantities of fine dust particles that are lifted into the atmosphere by strong winds and transported thousands of miles from their sources. This dust affects the atmospheric radiation balance by scattering and absorbing sunlight, generally producing a slight cooling effect on global temperatures. Dust particles also serve as condensation nuclei for cloud droplets, affecting cloud properties and precipitation patterns in regions far from the dust sources. Iron-rich dust from some desert regions provides essential nutrients for marine phytoplankton in parts of the ocean where these nutrients are otherwise scarce. Changes in dust production and transport therefore create connections between terrestrial and marine ecosystems that can influence global climate regulation. The Sahara Desert, for example, is a major source of dust that fertilizes the Amazon rainforest and supports marine productivity in the Atlantic Ocean. Satellite measurements show that approximately 40 million tons of dust travel from the Sahara to the Amazon each year, providing phosphorus and other nutrients that support the growth of one of Earth's most important terrestrial ecosystems. This transcontinental dust transport demonstrates how local environmental conditions in one region can influence climate regulation processes on the opposite side of the planet. Lightning represents another subtle but important connection between atmospheric processes and climate regulation. Lightning produces nitrogen compounds that act as fertilizers when they reach the ground, affecting plant growth and carbon uptake in terrestrial ecosystems. Lightning also produces ozone and other reactive compounds that affect atmospheric chemistry and the greenhouse effect. The frequency and intensity of lightning depend on atmospheric temperature, humidity, and instability, creating feedback loops between climate conditions and atmospheric chemistry. Warmer, more humid conditions generally favor more frequent lightning, potentially increasing the production of nitrogen fertilizers and ozone. These lightning climate feedbacks operate on regional scales and contribute to the complex web of interactions that maintain atmospheric composition. Thunder, the acoustic signature of lightning, provides a reminder of the enormous energies involved in atmospheric processes. Each lightning stroke releases energy equivalent to burning several gallons of gasoline in a fraction of a second, demonstrating the power contained in atmospheric electricity. Yet this dramatic energy release represents only a tiny fraction of the total energy flowing through Earth's climate system every day. The aurora, those beautiful displays of colored light in polar skies, reveal another connection between Earth's climate system and space weather. When charged particles from the solar wind interact with Earth's magnetic field and atmosphere, they create the shimmering curtains of light that have inspired human cultures throughout history. These interactions also affect atmospheric chemistry in polar regions, contributing to ozone destruction and other chemical processes that influence climate regulation. Seasonal variations in aurora activity reflect changes in solar wind conditions and Earth's magnetic field orientation, creating annual cycles in polar atmospheric chemistry. These cycles interact with seasonal changes in sunlight and temperature to create complex patterns of atmospheric composition that contribute to climate regulation in polar regions. The stratospheric ozone layer provides crucial protection for Earth's surface from harmful ultraviolet radiation, while also contributing to climate regulation through its absorption of both ultraviolet and infrared radiation. Ozone formation and destruction in the stratosphere involve complex photochemical reactions that respond to changes in solar radiation, atmospheric composition, and temperature. The discovery of the Antarctic ozone hole in the 1980s demonstrated how human activities could disrupt these stratospheric regulatory mechanisms, but it also showed how international cooperation could address global environmental problems. The successful reduction in ozone-depleting substances has allowed the ozone layer to begin recovering, illustrating the capacity for both disruption and restoration in Earth's regulatory systems. Atmospheric pressure systems create another layer of climate regulation through their effects on weather patterns and heat transport. High and low pressure systems form in response to temperature differences and Earth's rotation, creating the familiar weather patterns that distribute heat and moisture across regional scales. These pressure systems are constantly forming, moving, and dissipating, creating a dynamic atmospheric circulation that prevents any region from experiencing stagnant conditions for extended periods. The jet streams, rivers of fast-moving air in the upper atmosphere, play particularly important roles in heat transport and weather pattern organization. These high-altitude winds form along boundaries between air masses of different temperatures and help organize storm systems and weather patterns across entire continents. Changes in jet stream patterns can affect regional climate conditions for weeks or months, demonstrating how atmospheric circulation creates connections between distant regions. Pressure systems also affect ocean circulation through their influence on surface winds, which drive ocean currents and upwelling patterns. The trade winds, generated by pressure differences between high and low pressure systems, drive some of the most important ocean currents and upwelling zones that bring nutrients to the surface and support marine ecosystems. Evaporation and condensation create continuous exchanges of energy and water between Earth's surface and atmosphere. Every molecule of water that evaporates carries energy from the surface into the atmosphere, where that energy may be transported great distances before being released through condensation. This evaporation-condensation cycle represents one of the most efficient heat transport mechanisms in Earth's climate system. The energy involved in these phase changes of water is enormous. The evaporation of just 1 gram of water requires about 2,260 joules of energy, equivalent to the energy needed to heat that same gram of water from freezing to boiling. When that water vapor condenses back into liquid form, it releases the same amount of energy, warming the surrounding air. This latent heat transport moves energy equivalent to many times the total global energy consumption of human civilization. Humidity patterns around the world reflect the operation of this global evaporation condensation system. Desert regions, where evaporation exceeds precipitation, tend to be dry, while tropical regions, where precipitation exceeds evaporation, tend to be humid. These humidity patterns create comfortable or uncomfortable conditions for human life, but they also affect local energy balances through their influence on evaporation rates and cloud formation. The dew point, the temperature at which water vapor begins to condense out of the air, provides a measure of atmospheric energy content that weather forecasters use to predict storm development and comfort levels. High dew points indicate that the atmosphere contains large amounts of energy in the form of water vapor, energy that can be released rapidly during storm formation to create severe weather events. Precipitation patterns create the geographic distribution of freshwater resources that support terrestrial ecosystems and human civilization. The location and timing of precipitation depend on atmospheric circulation patterns, topography, and the availability of moisture sources, creating complex regional patterns that have remained relatively stable over long periods, despite year-to-year variations. Monsoon systems represent some of the most dramatic examples of seasonal precipitation patterns driven by thermal contrasts between land and ocean surfaces. During summer, intense heating of large landmasses creates low-pressure systems that draw moist air from adjacent oceans, creating the heavy rains that support agriculture and ecosystems across large regions of Asia, Africa, and Australia. These monsoon systems demonstrate how climate regulation operates across a spectrum of spatial and temporal scales. Local heating and cooling create regional pressure patterns, which organize atmospheric circulation over continental scales, which affects precipitation patterns that influence ecosystem function and carbon cycling over seasonal and annual timescales. Snow and ice create seasonal and longer-term variations in surface reflectivity that affect energy balance over regional and global scales. Fresh snow can reflect up to 95% of incoming solar radiation, while bare soil or vegetation typically reflects only 10 to 30%. The seasonal advance and retreat of snow cover therefore creates large changes in regional energy absorption that contribute to seasonal temperature patterns. Permafrost, permanently frozen ground in high-latitude regions, represents a vast reservoir of frozen organic matter that affects both local and global climate regulation. Permafrost soils contain more carbon than the entire atmosphere, stored in organic matter that has accumulated over thousands of years in frozen conditions that prevent rapid decomposition. As global temperatures warm, some permafrost regions are beginning to thaw, allowing decomposition to resume and releasing both carbon dioxide and methane to the atmosphere. This permafrost carbon feedback represents one of the most significant potential amplifying mechanisms in the current climate system, capable of adding substantial amounts of greenhouse gases to the atmosphere over coming decades and centuries. Yet even this potentially destabilizing process operates within the broader context of Earth's regulatory systems. The carbon released from thawing permafrost becomes available for uptake by vegetation growing in warming Arctic regions. Changes in vegetation cover affect surface energy balance and evapotranspiration rates. These vegetation changes may partially offset the warming effects of permafrost carbon release, demonstrating how regulatory mechanisms continue to operate even during periods of rapid change. Soil systems throughout the world participate in climate regulation through their storage of organic carbon and their influence on plant growth and water cycling. Healthy soils contain enormous amounts of carbon in the form of decomposed plant and animal material, often holding more carbon per unit area than the vegetation growing above them. The carbon content of soils depends on the balance between the input of organic matter from plant growth and the loss of carbon through decomposition and erosion. Climate conditions affect both sides of this balance, influencing both plant productivity and decomposition rates. Changes in temperature and precipitation can therefore affect soil carbon storage, creating feedback loops between climate and terrestrial carbon cycling. Soil microorganisms play crucial roles in these carbon cycling processes through their decomposition of organic matter and their relationships with plant roots. These tiny organisms respond to changes in temperature, moisture, and soil chemistry, adjusting their activity in ways that affect both carbon cycling and plant nutrition. The soil ecosystem represents one of Earth's most diverse and active biological communities, with profound effects on climate regulation. Root systems extend the influence of terrestrial vegetation deep into the soil, where they affect water movement, nutrient cycling, and soil structure. Deep-rooted plants can access groundwater during dry periods, maintaining photosynthesis and evapotranspiration when surface water is scarce. These deep root systems also help maintain soil structure and prevent erosion, protecting the soil carbon reservoir that contributes to climate regulation. Mycorrhizal fungi form partnerships with plant roots that extend the effective reach of root systems and improve plant access to nutrients and water. These fungal networks can connect different plants, allowing them to share resources and information in ways that improve their collective survival and growth. The mycorrhizal networks that connect forest ecosystems may help maintain forest stability and carbon storage capacity during environmental changes. Decomposition processes in soils and ecosystems represent the other side of the biological carbon cycle, returning carbon from organic matter back to the atmosphere. Decomposition rates depend on temperature, moisture, oxygen availability, and the chemical composition of the organic matter being decomposed. These factors create complex patterns of decomposition that vary geographically and seasonally. In cold or dry conditions, decomposition proceeds slowly, allowing organic matter to accumulate in soils and creating long-term carbon storage. In warm, moist conditions, decomposition proceeds rapidly, quickly returning carbon to the atmosphere, but also releasing nutrients that support new plant growth. The balance between these different decomposition regimes affects the global distribution of soil carbon and its response to climate changes. Wetland ecosystems demonstrate particularly complex interactions between hydrology, biology, and climate regulation. The waterlogged conditions in wetlands slow decomposition and promote the accumulation of organic matter in soils, creating some of Earth's most carbon-rich ecosystems. But the same anaerobic conditions that preserve soil carbon also promote the production of methane, a potent greenhouse gas. The climate regulation effects of wetlands therefore depend on the balance between carbon storage and methane emissions, a balance that can shift with changes in water levels, temperature, and ecosystem management. Wetlands also affect regional climate through their influence on local humidity and temperature, often creating cooler, more stable microclimates than surrounding upland areas. Peatlands represent an extreme example of wetland carbon accumulation, with some peat deposits containing thousands of years of accumulated organic matter. These ecosystems have removed enormous amounts of carbon from the atmosphere over long periods, creating thick deposits of partially decomposed plant material that can persist for millennia under the right conditions. The stability of peatland. Decarbon storage depends on maintaining the specific hydrological and chemical conditions that have allowed these systems to accumulate carbon over such long periods. Changes in precipitation patterns or temperature could alter these conditions, potentially converting peat deposits from carbon sinks into carbon sources. The global nitrogen cycle operates alongside the carbon cycle to influence plant growth and ecosystem function around the world. Nitrogen is an essential nutrient for all living organisms, but most of the nitrogen in our atmosphere exists in a form that plants cannot use directly. Specialized bacteria in soils and root systems convert atmospheric nitrogen into forms that plants can absorb, supporting the plant growth that removes carbon dioxide from the atmosphere. Lightning also contributes to nitrogen cycling by creating nitrogen compounds in the atmosphere that eventually reach the ground as natural fertilizer. This atmospheric nitrogen fixation represents a connection between weather processes and ecosystem nutrition that has operated throughout Earth's history. The energy released in lightning strikes transforms the stable nitrogen gas in our atmosphere into reactive compounds that support life across the planet. Phosphorus cycling operates on different timescales than carbon and nitrogen cycling because phosphorus has no significant atmospheric reservoir. Instead, phosphorus cycles slowly between rocks, soils, living organisms, and ocean sediments. The weathering of phosphorus-containing rocks provides this essential nutrient to terrestrial ecosystems, while rivers carry dissolved phosphorus to the oceans where it supports marine life. The slow cycling of phosphorus through the Earth system creates long-term constraints on ecosystem productivity and carbon cycling. Regions with abundant phosphorus can support more plant growth and carbon storage than regions where phosphorus is scarce. This nutrient limitation creates another regulatory mechanism in Earth's climate system, preventing runaway biological processes while maintaining steady ecosystem function. Ocean chemistry reflects the integrated effects of all these biogeochemical cycles. As rivers carry dissolved substances from the continents to the sea, the composition of seawater has remained remarkably stable over geological time, despite the continuous input of materials from weathering and the continuous removal of materials through biological processes and sedimentation. This stability in ocean chemistry emerges from the balance between inputs and outputs of various substances, a balance maintained by the same regulatory mechanisms that maintain atmospheric composition. When inputs of a particular substance increase, biological or chemical processes typically respond by removing more of that substance from seawater. When inputs decrease, removal processes slow down, maintaining overall chemical balance. The pH of seawater, its level of acidity or alkalinity, represents one of the most important aspects of ocean chemistry for marine life and climate regulation. The ocean's pH is buffered by dissolved carbonate compounds that resist changes in acidity, much like the buffering systems in our own blood that maintain stable conditions for life. This ocean pH buffering system has absorbed much of the excess carbon dioxide released by human activities, preventing even larger increases in atmospheric carbon dioxide concentrations. But this absorption of carbon dioxide gradually makes seawater more acidic, potentially affecting marine organisms that build shells and skeletons from calcium carbonate compounds. The deep ocean contains much older water masses that carry the chemical signatures of past climate conditions. These deep waters formed at the surface decades to centuries ago and have been isolated from the atmosphere during their slow journey through the ocean depths. Changes in surface climate conditions therefore take many decades to fully penetrate to the deep ocean, creating a lag in the ocean's response to atmospheric changes. This ocean inertia provides crucial stability to Earth's climate system by buffering rapid changes in atmospheric conditions, but it also means that changes already set in motion will continue to influence climate for many decades or centuries, even if atmospheric conditions stabilize. The ocean's thermal and chemical memory extends far beyond human timescales, connecting past and future climate conditions through the slow circulation of deep waters. Hydrothermal vents on the ocean floor create unique ecosystems that operate independently of sunlight, deriving energy from chemical reactions between seawater and hot rocks. These deep-sea ecosystems demonstrate that life can thrive under conditions very different from those at Earth's surface, using energy sources that have been available throughout Earth's history. The chemical processes at hydrothermal vents also contribute to ocean chemistry and climate regulation by affecting the cycling of various elements between the ocean and solid Earth. Hot water circulating through oceanic crust leaches some elements from rocks while depositing others, creating chemical exchanges that operate over geological timescales. Mid-ocean ridges, where new oceanic crust forms through seafloor spreading, create additional connections between Earth's interior and surface climate system. As magma rises and solidifies at these underwater mountain ranges, it releases heat and gases that affect local ocean chemistry and biology. The formation of new oceanic crust also affects global sea level and ocean basin geometry over geological time. Subduction zones, where oceanic plates descend into Earth's interior, complete the tectonic cycle by recycling oceanic crust and its accumulated sediments back into the mantle. This process carries water and other surface materials into Earth's interior, where they may eventually be returned to the surface through volcanic activity. The subduction process also generates the volcanic arcs and mountain ranges that affect regional and global climate patterns. The rock cycle connects all of these tectonic processes through the continuous transformation of rocks between igneous, sedimentary, and metamorphic forms. Each transformation involves different temperature and pressure conditions and different interactions with water and atmospheric gases. The rock cycle therefore creates pathways for materials to move between Earth's surface and interior over geological timescales. Sedimentary rocks preserve records of past climate conditions in their layers, grain sizes, and fossil content. These geological archives reveal that Earth's climate has varied significantly throughout geological history, while remaining within the range that supports liquid water and complex life. The sedimentary record shows both the operation of regulatory mechanisms and the limits of their effectiveness during extreme events. Metamorphic rocks form when existing rocks are subjected to high temperatures and pressures without melting completely. This process can release or consume gases and water, affecting atmospheric and oceanic composition over geological timescales. Mountain-building events that create extensive metamorphic rock formations therefore contribute to long-term climate regulation through their effects on atmospheric chemistry. Igneous rocks form when molten material crystallizes, either at Earth's surface through volcanic activity or deep within the crust and mantle through slow cooling of magma bodies. The formation of igneous rocks involves the release of gases and heat that can affect atmospheric composition and climate over various timescales, from the immediate effects of individual eruptions to the long-term effects of major magmatic events. Mineral formation and dissolution create the detailed chemical processes that drive many of Earth's regulatory mechanisms. Each mineral has specific stability conditions and reacts with water and atmospheric gases in predictable ways. The formation of clay minerals during weathering, for example, consumes atmospheric carbon dioxide while creating minerals that can store water and nutrients for plant growth. Crystal structures in minerals determine how they interact with their environment and how stable they are under different conditions. The same chemical elements can form different minerals with different properties depending on temperature, pressure, and the presence of other substances. This mineral diversity creates multiple pathways for chemical reactions that contribute to climate regulation. Soil formation integrates weathering, biological activity, and climate conditions over timescales of centuries to millennia. Different climate conditions produce different soil types with different properties and different capacities for storing carbon and supporting plant growth. The global distribution of soil types therefore reflects both current and past climate conditions. Soil profiles reveal the history of climate and ecosystem conditions through their layered structure and chemical composition. Each layer represents different periods of soil formation under different environmental conditions. These soil archives provide information about past climate conditions and ecosystem responses that complement the records preserved in lake sediments, tree rings, and ice cores. Erosion processes move soil and rock materials from higher to lower elevations, gradually wearing down mountains and filling ocean basins with sediment. These erosion processes are influenced by climate conditions, particularly precipitation patterns and temperature cycles that affect weathering rates and vegetation cover. Climate and erosion therefore interact through complex feedback loops over geological timescales. Landscape evolution reflects the balance between tectonic uplift, which raises rocks above sea level, and erosion, which gradually wears them down. Different climate conditions produce different erosion rates and different landscape forms. Humid climates tend to produce rounded, soil-covered hills, while arid climates tend to produce steep, rocky slopes with thin soils. River systems evolve in response to both tectonic and climatic influences, carving valleys and transporting sediment from continents to oceans. The patterns of river networks reflect the balance between water flow, which tends to create straight channels, and the underlying geology, which creates obstacles and variations in rock resistance. These river patterns influence regional climate through their effects on local humidity and temperature. Glacial landscapes preserve evidence of past ice ages in their distinctive landforms created by moving ice. Glacial valleys, moraines, and polished rock surfaces reveal where ice sheets and glaciers once existed, providing information about past climate conditions. These glacial landforms continue to influence local climate and hydrology long after the ice has retreated. Coastal landscapes demonstrate the interactions between sea level, climate, and geological processes. Beaches, cliffs, and coastal wetlands respond to changes in sea level, storm intensity, and sediment supply, all of which are influenced by climate conditions. Coastal environments also affect regional climate through their influence on local humidity and temperature patterns. Desert landscapes show how life and geological processes adapt to extreme climate conditions. Desert soils, rock formations, and occasional vegetation create distinctive patterns that minimize water loss while maximizing the use of scarce precipitation. These desert adaptations demonstrate the resilience of Earth's systems under challenging conditions. Tropical landscapes reveal the effects of abundant warmth and moisture on geological and biological processes. Thick soils, rapid weathering, and luxuriant vegetation characterize tropical regions, creating landscapes that actively participate in climate regulation through their high rates of photosynthesis and evapotranspiration. Arctic landscapes show how life and geological processes respond to cold conditions and seasonal extremes. Permafrost, seasonal freezing and thawing, and specialized vegetation create distinctive patterns that store large amounts of carbon while operating under challenging temperature conditions. Mountain landscapes demonstrate how altitude creates diverse climate conditions within small geographic areas. Temperature, precipitation, and vegetation change dramatically with elevation, creating multiple climate zones stacked vertically. These elevation gradients provide natural laboratories for understanding how climate conditions affect geological and biological processes. Valley systems often create their own local climate patterns through their effects on airflow, temperature, and moisture retention. Cold air drainage, fog formation, and temperature inversions in valleys create microclimates that can differ significantly from surrounding areas. These local climate patterns affect vegetation, soil development, and erosion processes. Plateau regions demonstrate how flat, elevated terrain interacts with climate systems. High plateaus often experience different precipitation and temperature patterns than surrounding lowlands, creating distinctive ecosystems and climate conditions. The Tibetan Plateau, for example, influences monsoon patterns across much of Asia through its effects on atmospheric circulation. Island climates show how isolation and ocean influence create distinctive environmental conditions. Islands often experience more stable temperatures than continental areas at similar latitudes because of the moderating influence of surrounding ocean water. Island ecosystems also demonstrate how isolation affects evolution and ecosystem development. Archipelago systems create complex patterns of climate and ecosystem variation across multiple islands with different sizes, elevations, and distances from other landmasses. These island chains provide natural experiments in how geographic factors influence climate and biological processes. Continental interiors experience more extreme temperature variations than coastal areas because they lack the moderating influence of large water bodies. These continental climates create distinctive seasonal patterns and ecosystem adaptations that differ from those in maritime climates. Peninsular regions experience intermediate climate conditions between fully continental and fully maritime environments. The width and orientation of peninsulas affect how much oceanic influence reaches their interior areas, creating gradients in climate conditions and ecosystem types. Coastal plains often experience distinctive climate patterns created by their low elevation and proximity to large water bodies. Sea breezes, fog formation, and storm effects create climate conditions that support unique ecosystems and agricultural systems. River valleys create linear corridors of distinctive climate conditions that often extend far inland from coastal areas. Rivers transport moisture and moderate temperatures, creating ribbons of more favorable climate conditions that support different vegetation and wildlife than surrounding uplands. Mountain valleys often trap cold air and moisture, creating climate conditions that differ from both the surrounding lowlands and the adjacent mountain slopes. These valley climates can support distinctive ecosystems and create local weather patterns that influence regional climate systems. Intermountain basins demonstrate how topographic barriers create isolated climate systems with limited connections to surrounding areas. These basins often experience distinctive precipitation and temperature patterns that create unique ecosystems and climate conditions. Badlands and other eroded landscapes show how geological processes create landforms that influence local climate patterns. The complex topography of badlands creates diverse microclimates within small areas, demonstrating how surface roughness affects airflow and temperature patterns. Karst landscapes, formed by the dissolution of limestone and other soluble rocks, create distinctive hydrology and climate patterns. Underground rivers, caves, and disappearing streams create water cycles that differ from those in other landscapes, affecting local humidity and temperature patterns. Volcanic landscapes demonstrate how geological activity creates distinctive climate and ecosystem conditions. Fresh volcanic soils, geothermal heat, and unique topography create environmental conditions that support distinctive plant and animal communities while influencing local weather patterns. Sand dune systems show how wind patterns and sediment supply create dynamic landscapes that continuously change shape while maintaining overall patterns. Dune fields affect local climate through their influence on airflow and temperature, while their movement can alter regional drainage and vegetation patterns. Salt lakes and playas demonstrate how closed drainage basins concentrate dissolved minerals and create extreme environmental conditions. These salt-rich environments support specialized ecosystems while affecting local climate through their high reflectivity and lack of evapotranspiration. Wetland complexes create distinctive hydrology and climate patterns through their effects on water storage, evaporation, and local humidity. Large wetland systems can influence regional precipitation patterns and moderate local temperature extremes while supporting diverse ecosystems. Floodplains demonstrate how periodic flooding creates distinctive soils and ecosystems while influencing regional hydrology and climate. The seasonal cycle of flooding and drying creates unique environmental conditions that many species have adapted to over evolutionary time. Estuaries show how the mixing of fresh and salt water creates unique chemical and biological conditions that affect local climate and ecosystem function. These transitional environments often support high biological productivity while influencing coastal climate patterns. Deltas demonstrate how river-borne sediments create new land while influencing coastal and marine ecosystems. Delta formation affects sea level patterns, coastal protection, and regional hydrology while supporting distinctive ecosystems adapted to changing water levels and sediment deposition. Continental shelves extend the influence of terrestrial processes into marine environments while affecting coastal climate and ecosystem patterns. Shallow shelf waters often support high biological productivity while influencing coastal weather patterns and storm impacts. Deep ocean basins demonstrate how isolated water masses develop distinctive chemical and biological characteristics over long periods. These deep water environments affect global ocean circulation while supporting unique ecosystems adapted to high pressure and low temperature conditions. Ocean ridges create unique geological and biological environments while affecting global sea level and ocean chemistry. The heat and chemical inputs from ridge systems influence ocean circulation and support distinctive ecosystems that derive energy from chemical processes rather than sunlight. Ocean trenches represent the deepest parts of Earth's surface while playing important roles in global tectonics and ocean chemistry. The extreme conditions in ocean trenches support specialized ecosystems while affecting the cycling of materials between Earth's surface and interior. Seamounts and underwater mountains create obstacles to ocean flow while supporting distinctive marine ecosystems. These underwater peaks affect regional ocean circulation while providing habitat for species that require hard surfaces in the deep ocean environment. Abyssal plains represent the vast, flat areas of the deep ocean floor, where sediments from continents and marine organisms accumulate over geological time. These quiet environments preserve detailed records of past climate and ocean conditions, while supporting ecosystems adapted to extremely stable conditions. Hydrothermal vent fields create oases of biological activity in the deep ocean while demonstrating how chemical energy can support complex ecosystems. These vent communities provide insights into how life might exist under extreme conditions while contributing to ocean chemistry through their metabolic processes. Cold seeps show how slow chemical processes can support biological communities over long periods without the dramatic activity of hot hydrothermal vents. These seep environments demonstrate the diversity of ways that chemical energy can support life while affecting local ocean chemistry. Coral reefs represent some of the most diverse and productive ecosystems on Earth while actively participating in ocean chemistry through their formation of calcium carbonate structures. These reef systems create complex three-dimensional habitats while affecting local ocean circulation and coastal protection. Kelp forests demonstrate how marine vegetation can create complex ecosystems while affecting local ocean chemistry and physics. These underwater forests provide habitat for diverse marine life while influencing water flow, light penetration, and nutrient cycling. Polar ice environments create unique conditions that affect global climate while supporting specialized ecosystems adapted to extreme cold. Sea ice, ice sheets, and glaciers all contribute to climate regulation while providing habitat for species that depend on ice-related environments. As we reach toward the completion of this gentle exploration, we find ourselves surrounded by the quiet majesty of Earth's regulatory systems operating in perfect harmony across scales both intimate and vast. Every breath we take connects us to an atmosphere that has been maintained in life-supporting balance for billions of years through the elegant interplay of simple physical laws. The carbon atoms we exhale today may once have been part of ancient limestone, dissolved in prehistoric oceans, or locked in the wood of trees that grew when dinosaurs walked the earth. These same atoms will continue their patient journey through Earth's regulatory cycles long after we are gone, participating in the same chemical processes that have maintained our planet's habitability across deep time. The water that flows through our bodies connects us to the global water cycle that has been redistributing heat and moisture around our planet since the oceans first formed. This water may have fallen as rain on distant mountains, flowed through underground aquifers, or evaporated from tropical seas before becoming part of us for this brief moment in its eternal circulation. The oxygen in our blood was produced by photosynthesis, the same process that has been removing carbon dioxide from our atmosphere for over 3 billion years. Every breath we take represents a gift from the countless plants and marine organisms that continue to maintain atmospheric composition within the narrow range that complex life requires. The stable temperature that allows us to exist emerges from the same energy balance that has regulated Earth's climate throughout its history. Solar energy arriving from our nearest star, greenhouse gases that trap just enough heat, and radiative cooling that prevents runaway warming all work together through simple physical processes that require no guidance or intervention. The solid ground beneath us moves imperceptibly slowly as continents drift across Earth's surface, driven by heat from our planet's interior. This movement, barely detectable over human lifetimes, has shaped climate patterns over geological time while providing the volcanic activity and mountain building that participate in long-term climate regulation. The oceans that cover most of our planet's surface continue their slow, majestic circulation, carrying heat from equator to poles and storing vast amounts of thermal energy that buffer rapid climate changes. This circulation operates according to the same principles of density and pressure that govern all fluid motion, scaled up to planetary proportions. In contemplating these vast, interconnected systems, we discover not chaos or randomness, but deep order emerging from simple rules applied consistently across space and time. Gravity shapes the circulation of both atmosphere and oceans. Electromagnetic radiation from the sun provides the energy that drives photosynthesis, evaporation, and weather patterns. Chemical bonds form and break in predictable ways that create the biogeochemical cycles maintaining atmospheric composition. No consciousness or intention guides these processes. They arise naturally from the fundamental properties of matter and energy, creating a self-organizing system that maintains the conditions necessary for the extraordinary complexity and beauty of life. In this understanding, we find not just scientific knowledge, but profound peace in recognizing our place within a universe whose very physics conspire to create and maintain the conditions for our existence. The same laws that govern the behavior of atoms and molecules also govern the circulation of oceans and atmosphere. The same thermodynamic principles that determine how heat flows through materials also determine how energy moves through Earth's climate system. The same chemical reactions that occur in laboratory beakers also occur in soils, oceans, and living organisms across our planet. This unity of physical law creates connections across all scales of Earth's regulatory systems. The quantum mechanical properties that determine how molecules interact with radiation create the greenhouse effect that maintains Earth's temperature. The atomic structure of carbon allows it to form the complex molecules of life, while participating in the chemical cycles that regulate atmospheric composition. Water's unique molecular properties, determined by the quantum mechanics of chemical bonding, create its remarkable ability to dissolve other substances, moderate temperature changes, and exist in all three phases under Earth's surface conditions. These molecular properties make possible the water cycle that redistributes heat around our planet and supports all known life. The nuclear reactions in our Sun's core follow the same quantum mechanical principles that govern chemical reactions on Earth, creating the steady energy source that has powered Earth's climate system for billions of years. The gradual increase in solar energy output over geological time has been accommodated by Earth's regulatory mechanisms, maintaining habitable conditions as our star slowly evolves. Even the formation of our solar system followed predictable physical processes as gravity gathered cosmic dust and gas into the Sun, planets, and smaller bodies that make up our cosmic neighborhood. The same gravitational forces that formed Earth continue to maintain its orbit and rotation, providing the stable astronomical foundation for all climate processes. The radioactive decay of elements in Earth's interior, governed by quantum mechanical processes, provides the heat that drives plate tectonics and volcanic activity. This internal heat source has remained relatively steady over geological time, providing consistent energy for the tectonic processes that participate in long-term climate regulation. As we rest in this knowledge, we can feel ourselves as integral parts of these vast, harmonious systems. Our bodies are temporary organizations of atoms and molecules that participate in the same chemical and physical processes that regulate Earth's climate. Our metabolism connects us directly to the carbon cycle, the water cycle, and the energy flows that maintain planetary habitability. The warmth of our bodies emerges from the same chemical processes that release energy from organic matter in soils and ecosystems around the world. The water in our cells participates in the same molecular interactions that create clouds, rain, and ocean currents. The carbon dioxide we exhale joins the atmospheric reservoir that plants use for photosynthesis and that slowly cycles through rocks and oceans over geological time. Our consciousness, that remarkable property that allows us to understand and appreciate these systems, emerges from the complex organization of matter and energy that Earth's regulatory systems have made possible. The stable conditions maintained by these systems have allowed the evolution of brains capable of comprehending the very processes that created them. In this recognition, we find both humility and wonder. We are neither separate from nor controlling these planetary systems, but rather temporary expressions of the same physical processes that create weather, seasons, and the cycling of elements through Earth's spheres. Our brief existence allows us to witness and appreciate the magnificent regulatory systems that have maintained habitability for billions of years. The night sky above us reveals the cosmic context within which Earth's regulatory systems operate. The stars we see represent other suns, following the same nuclear processes that power our own star. Some of those stars may warm planets with their own regulatory systems, their own unique solutions to the challenge of maintaining stable conditions suitable for complexity and perhaps life. The darkness between stars represents the vast, cold universe into which Earth radiates heat every moment, maintaining the energy balance that keeps our planet habitable. This cosmic backdrop emphasizes the remarkable nature of Earth's regulatory systems, which create and maintain a warm, stable oasis of complexity in an otherwise cold and largely empty universe. As sleep approaches, we can find deep comfort in knowing that these regulatory systems will continue their patient work throughout the night and for countless nights to come. The atmosphere will continue its slow circulation, redistributing heat and moisture. The oceans will continue their majestic thermohaline circulation, storing and transporting thermal energy. The chemical cycles will continue their molecular scale work, maintaining the atmospheric composition that makes each breath possible. These systems require nothing from us to continue their essential functions. They arise naturally from the fundamental properties of matter and energy, operating according to the same physical laws that govern everything from the smallest atoms to the largest galaxies. In recognizing this natural order, we can release any sense of burden or responsibility for maintaining planetary systems that are far greater and more enduring than our individual lives. Instead, we can rest peacefully in the knowledge that we are held and supported by systems whose stability spans geological time. The same processes that maintained Earth's habitability through the rise and fall of countless species, through ice ages and warm periods, through asteroid impacts and massive volcanic eruptions, continue to operate today with the same quiet efficiency they have shown throughout Earth's history. Tomorrow's sunrise will bring solar energy that has travelled 93 million miles to warm our planet, just as it has every day for billions of years. That energy will drive evaporation from the oceans, creating water vapour that will rise into the atmosphere and eventually fall as precipitation that nourishes life and shapes landscapes. Plants will use that same solar energy to perform photosynthesis, removing carbon dioxide from the atmosphere while releasing the oxygen that makes complex life possible. These processes will continue with or without our attention or understanding, driven by the elegant simplicity of physical law applied across the complexity of planetary systems. Yet our capacity to understand and appreciate these systems adds something beautiful to the universe, a consciousness capable of recognizing the remarkable achievement that Earth represents in creating and maintaining conditions suitable for awareness itself. As we drift towards sleep, we can imagine ourselves as part of this vast, interconnected system, our bodies maintaining their own internal regulation through processes that mirror those operating at planetary scales. Our heartbeat distributes nutrients and energy throughout our bodies, much as ocean currents distribute heat throughout the planet. Our breathing exchanges gases with the atmosphere, connecting our metabolism to the global cycles that maintain atmospheric composition. In sleep, our conscious minds rest while our bodies continue their automatic regulatory functions, maintaining stable internal conditions through mechanisms we neither control nor need to understand. This personal experience of natural regulation, operating below the level of consciousness, mirrors the planetary regulatory systems that maintain Earth's habitability through processes that require no awareness or intention. The gentle rhythm of breathing that carries us towards sleep connects us directly to the atmospheric reservoir that has been maintained in life-supporting balance for billions of years. Each exhale releases carbon dioxide that may be absorbed by a distant forest or dissolved in the ocean. Each inhale brings oxygen produced by photosynthesis somewhere else on our planet, connecting us through the atmosphere to the global community of life. The warmth that keeps us comfortable as we rest emerges from the same energy balance that maintains Earth's temperature within the narrow range that allows liquid water to exist. Our body heat represents a tiny portion of the energy flowing through Earth's systems every moment, energy that ultimately derives from nuclear reactions in our sun's core and radiates back to space through the same processes that have regulated planetary temperature throughout geological time. As consciousness fades into the peace of sleep, we remain held and supported by regulatory systems whose patience and persistence dwarf human experience. These systems will continue their work through the night, through all our nights, and for millions of years beyond human existence, maintaining the conditions that make complexity and beauty possible in our corner of the universe. In this understanding, we find the deepest peace available to conscious beings. The recognition that we exist within systems far greater than ourselves, systems whose stability and endurance provide the foundation for everything we cherish about existence. We are temporary expressions of the same physical processes that maintain the conditions for wonder and awareness. Brief flickerings of consciousness in a universe governed by timeless physical laws. The morning will bring new cycles within the eternal patterns that have sustained our planet for eons. Dew will form on grass as water vapor condenses in the cooling night air, demonstrating the same phase transitions that create clouds and precipitation on global scales. The sun will rise and warm the eastern horizon, beginning another day in the endless rhythm of heating and cooling that drives atmospheric circulation and weather patterns around the world. Birds will sing in trees that are quietly performing photosynthesis, using solar energy to combine atmospheric carbon dioxide with water to create the organic molecules that form their tissues. This same process, occurring in countless plants across the planet, maintains the atmospheric oxygen concentration that allows complex life to thrive while removing carbon dioxide that would otherwise accumulate and alter Earth's energy balance. Somewhere in the ocean, phytoplankton will bloom in surface waters warmed by the morning sun. These microscopic marine organisms performing the same photosynthetic process as land plants, but floating freely in the vast aquatic realm that covers most of our planet's surface. Their collective activity influences both atmospheric composition and the formation of clouds over the oceans, demonstrating how even the smallest life forms participate in planetary climate regulation. Deep beneath the ocean's surface, cold, dense water will continue its slow journey from polar regions toward the equator, carrying dissolved gases and nutrients while transporting heat energy stored centuries ago when that water last touched the atmosphere. This deep circulation connects different eras of Earth's climate history, creating a living archive of past conditions while influencing present and future climate patterns. On distant continents, rivers will continue their patient work of chemical weathering, carrying dissolved minerals from the breakdown of rocks toward the sea. This process, operating grain by grain and molecule by molecule, removes carbon dioxide from the atmosphere over geological timescales while creating the sediments that will eventually form new rocks and complete the cycle of material exchange between Earth's surface and interior. In mountain ranges around the world, snow and ice will respond to the daily temperature cycle, melting slightly during warm afternoons and refreezing during cool nights. These small daily changes aggregate over seasons and years to create the longer-term patterns of glacial advance and retreat that reflect climate conditions while influencing regional water supplies and sea levels. Underground, in the darkness of soil and rock, countless microorganisms will continue their metabolic processes, breaking down organic matter and cycling nutrients between different chemical forms. These invisible communities perform essential functions in Earth's regulatory systems, mediating the exchange of gases between soils and atmosphere while supporting the plant growth that maintains atmospheric composition. In the planet's interior, molten rock will continue its slow convection, driven by heat from radioactive decay and the gradual cooling of Earth's core. This internal circulation drives the movement of continents across the surface while generating the volcanic activity that returns carbon dioxide from the deep Earth to the atmosphere, balancing the removal of carbon through weathering and sedimentation. The magnetic field generated by circulation in Earth's molten iron core will continue to deflect charged particles from the solar wind, protecting our atmosphere from erosion and maintaining the stable atmospheric composition that makes life possible. This invisible shield operates continuously, providing protection that we never see, but that remains essential for maintaining the habitability our planet has enjoyed for billions of years. Lightning will flash somewhere in the world, as electrical charges build up in storm systems, creating nitrogen compounds that will eventually reach the ground as natural fertilizer, while producing ozone that affects atmospheric chemistry. These dramatic electrical discharges represent the release of energy accumulated through atmospheric processes, demonstrating the vast energies contained within Earth's weather systems. Tides will rise and fall in their eternal rhythm, driven by gravitational interactions with the moon and sun. These regular water level changes mix ocean waters, transport nutrients, and affect coastal ecosystems, while demonstrating how astronomical forces participate in Earth's regulatory systems. The tidal mixing helps maintain ocean circulation patterns, while supporting marine life that depends on the regular cycling of nutrients and dissolved gases. Atmospheric pressure systems will continue their formation, movement, and dissipation, creating the weather patterns that distribute heat and moisture across regional scales. High-pressure areas will bring clear skies that allow maximum solar heating, while low-pressure systems will generate clouds and precipitation that provide cooling through increased reflection of sunlight and release of latent heat at high altitudes. Seasonal changes will progress at their unhurried pace as Earth continues its orbital journey around the Sun. The gradual shift in solar radiation patterns will trigger responses in vegetation, snow cover, and atmospheric circulation that create the annual rhythms within which shorter-term weather variations occur. These seasonal patterns provide predictable structure while accommodating the year-to-year variations that create weather's endless fascination. Volcanic activity will continue somewhere on Earth as magma generated by plate tectonic processes reaches the surface. Whether explosive or effusive, these volcanic events will release gases and heat while creating new rock formations that will eventually participate in chemical weathering reactions. Individual eruptions may temporarily affect regional or global climate, but the long-term pattern of volcanic activity helps maintain the chemical balance between Earth's interior and surface. Ecosystems will continue their complex interactions with climate through the countless individual organisms that respond to environmental conditions while collectively influencing those same conditions through their metabolic processes. Forests will continue transpiring water vapor while storing carbon in their woody tissues. Grasslands will continue their seasonal cycles of growth and dormancy while maintaining soil carbon through their extensive root systems. Desert organisms will continue their remarkable adaptations to extreme conditions while affecting regional climate through their influence on surface properties and dust emissions. Arctic and alpine species will continue their specialized existence in cold environments while participating in carbon cycling and other biogeochemical processes under challenging temperature conditions. Marine ecosystems will continue their complex food webs while influencing ocean chemistry and atmospheric composition through the collective metabolic activities of countless organisms, from microscopic plankton to large marine mammals. Coral reefs will continue building carbonate structures while supporting some of Earth's most diverse biological communities. Deep ocean communities will continue their existence in the eternal darkness of the abyss while processing organic matter that settles from surface waters. All of these processes will continue according to the same physical and chemical principles that have governed Earth systems throughout planetary history. No conscious control guides these interactions. No intention shapes these patterns. They emerge naturally from the fundamental properties of matter and energy, creating order and stability through the collective operation of countless individual processes, each following simple, predictable rules. The beauty of this natural order lies in its spontaneous emergence from basic physical laws. Gravity creates pressure gradients that drive atmospheric and oceanic circulation. Electromagnetic radiation from the sun provides energy that powers photosynthesis, evaporation, and weather systems. Chemical bonds form and break according to thermodynamic principles that determine which reactions occur under different environmental conditions. Temperature differences drive heat flow according to the laws of thermodynamics, creating the circulation patterns that distribute energy throughout Earth's systems. Density differences created by temperature and composition variations drive the circulation of both air and water, maintaining the global transport systems that moderate regional climate conditions. Phase transitions of water between vapor, liquid, and ice follow physical principles that determine how much energy is absorbed or released during each transformation. These energy exchanges create the latent heat transport that moves vast amounts of energy through the atmosphere, while the changing surface properties of ice, water, and vegetation create feedback loops that influence energy absorption and reflection. Chemical equilibria determine how gases dissolve in water and how minerals precipitate from solution, governing the cycling of elements between different reservoirs in Earth's systems. These equilibrium processes maintain the chemical balance of the oceans and atmosphere while responding to changes in temperature, pressure, and concentration that occur over various timescales. Biological processes operate according to biochemical principles that determine how organisms extract energy from their environment while influencing that environment through their metabolic activities. The evolution of these biological processes has created increasingly sophisticated ways for life to interact with and influence planetary systems, but always within the constraints imposed by physical and chemical laws. The integration of all these processes across multiple scales of space and time creates emergent properties that arise from their collective interactions, but cannot be predicted from understanding any single component alone. The stability of atmospheric composition emerges from the balance between countless processes that add and remove different gases. The maintenance of ocean chemistry emerges from equilibria between dissolution, precipitation, biological uptake, and physical transport. Climate stability emerges from the operation of feedback loops that tend to counteract changes in external conditions. When solar radiation increases, enhanced evaporation increases cloud cover that reflects more sunlight back to space. When atmospheric carbon dioxide increases, enhanced plant growth removes more carbon from the atmosphere, while increased weathering rates consume atmospheric carbon dioxide through chemical reactions with rocks. These stabilizing feedbacks operate automatically, without requiring any awareness or control. They represent the natural tendency of complex systems to maintain steady states when subjected to external perturbations. The same principles operate in many other natural systems, from the regulation of body temperature in warm-blooded animals to the maintenance of chemical concentrations in cells. Yet these regulatory mechanisms have limits, and under extreme conditions they can be overwhelmed, or may even operate in ways that amplify rather than dampen changes. The ice ages demonstrate how Earth's climate system can transition between different stable states when external conditions change sufficiently. The extreme greenhouse and icehouse climates of the geological past show how the regulatory systems can maintain habitability, even under conditions very different from those we experience today. The current climate state represents one point in the continuous evolution of Earth's regulatory systems as they respond to slowly changing external conditions and the evolution of life itself. The rise of oxygen-producing photosynthesis fundamentally altered atmospheric composition and climate regulation mechanisms billions of years ago. The evolution of land plants changed weathering rates and the carbon cycle. The evolution of marine organisms with calcium carbonate shells affected ocean chemistry and carbon cycling. Human activities now represent another influence on these ancient regulatory systems, adding greenhouse gases to the atmosphere at rates much faster than most natural processes, while altering land surfaces and ecosystems in ways that affect their climate regulation functions. Yet the fundamental regulatory mechanisms continue to operate according to the same physical and chemical principles that have governed them throughout Earth's history. The regulatory systems we've explored tonight continue their ancient work as we speak, following the same physical laws that have maintained Earth's habitability for billions of years. These processes require no guidance, no intention, no consciousness to operate. They emerge naturally from the fundamental properties of matter and energy, creating a self-organizing system of remarkable stability and resilience. From the gentle circulation of our atmosphere to the patient weathering of rocks, from the vast storage of heat in our oceans to the quiet cycling of carbon through living systems, every mechanism we've discovered operates according to simple, elegant physical principles. The same laws that govern the behavior of individual atoms also shape the circulation of entire ocean basins. The same energy that warms a single raindrop also drives the global patterns that distribute heat around our planet. In understanding these systems, we find profound comfort in recognizing that we exist within a universe whose fundamental physics naturally create and maintain the conditions for complexity, beauty, and life itself. Earth's temperature regulation represents not a miraculous exception to natural law, but rather its most magnificent expression. A demonstration of how simple rules, applied consistently across deep time, can create and sustain the extraordinary phenomenon we call home.